You are not standing still. Right now, as you watch this, you are moving at 1.3 million miles per hour through the universe, faster than any bullet, faster than any rocket humanity has ever launched, faster than anything we've ever built or measured or even imagined until we had the tools to prove it. And you feel none of it, not a whisper, not a tremor. The chair beneath you feels solid. The air around you seems calm. Your coffee sits motionless in its cup. Your brain has spent your entire life constructing a lie so convincing, so flawlessly executed, that you believe with total certainty you are sitting in one place. But you're not. You never have been. Earth is spinning at 1,000 miles per hour, while orbiting the Sun at 67,000. While the Sun drags our entire solar system around the Milky Way at over 500,000 miles per hour on a journey that takes 230 million years to complete, and the Milky Way itself is being pulled, tugged by something so massive, so impossibly large, that it warps the motion of millions of galaxies across hundreds of millions of light years. They call it the Great Attractor. We can't see it. It hides behind the disk of our own galaxy, cloaked in dust and distance. But we know it's there because we can measure its pull. And beyond that, there are hints, quiet anomalies in the data, suggestions that something even larger, something outside the observable universe, is pulling us toward a destination we can't see and may never reach. The stillness you feel is not real. It is a trick your nervous system plays so you can function, so you can walk and think and survive. But the truth written into the fabric of the cosmos itself, is that you have never stopped moving, and this is the story of where you're going. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in, this is going to be a good one. You are sitting still right now. You can feel the chair beneath you, solid and unmoving. Your coffee mug rests on the table exactly where you left it. The walls around you stand firm. The ground beneath the building holds steady. Everything in your immediate sensory universe tells you that you are stationary, that you have chosen to pause in a world that sometimes moves, but right now, in this moment, does not. That feeling is a lie, a useful one, an evolutionary necessity, but a lie nonetheless. Because at this exact moment, while you sit there convinced of your own stillness, you are screaming through space at speeds that would make a fighter pilot weep. You are moving so fast that if you could somehow step outside the reference frame you're trapped in, the velocity alone would pulverize you into a thin red mist before your brain had time to register what was happening. Let's start small. Let's start with the thing you're standing on. The Earth rotates. Everyone knows this. You learnt it in second grade, probably from a teacher who spun a globe on her desk and told you that's why we have day and night. Simple, obvious, boring even. But here's the part they didn't tell you, or if they did, you didn't process it the way you should have. The Earth rotates at approximately 1,000 miles per hour. 1,000 miles per hour. At the equator, the surface of the planet beneath your feet is moving at roughly 1,040 miles per hour. That's Mach 1.4. That's faster than the speed of sound. That's the velocity of a bullet fired from a high-powered rifle. And it's happening right now, smoothly, constantly, without pause, beneath every step you've ever taken. If you're not at the equator, the number drops. The speed of Earth's rotation depends on your latitude because the planet is a sphere. The closer you get to the poles, the smaller the circle you're tracing through space, and the slower your tangential velocity becomes. At 45 degrees north latitude, you're moving at about 700 miles per hour. At the poles themselves, you're barely rotating at all, just pivoting slowly in place like a figure skater pulling their arms in for a spin. But if you're anywhere near the equator, anywhere in the tropics, anywhere along the thick belt of the planet's waistline, you are moving faster than sound, right now. While you sit there, the Kennedy Space Center sits at about 28.5 degrees north latitude, just below Jacksonville, Florida. At that location, the ground is moving at roughly 914 miles per hour. NASA built the launch site there on purpose. When you're trying to throw a rocket into space, every bit of free velocity helps. By launching eastward from the Florida coast, engineers get to add the Earth's rotational speed to the rocket's velocity for free. It's the planet's way of giving the spacecraft a running start, a 900-mile-per-hour push before the engines even light. The rocket doesn't generate that speed. The Earth hands it over, a gift from a spinning globe, to anything brave or foolish enough to try to leave it. And you don't feel it. You don't feel any of it. You never have. You were born into this reference frame, moving at 1,000 miles per hour before you took your first breath, and every object around you, every molecule of air, every insect and bird and skyscraper and mountain, all of it is moving at the same speed in the same direction. There is no wind because the atmosphere rotates with the surface. There is no sense of motion because motion is only detectable relative to something else, and there is no something else. You are inside a system where everything moves together, and from inside that system, the system looks still. This is inertia doing exactly what Isaac Newton said it would do. An object in motion stays in motion unless acted upon by an external force. You are in motion. You have always been in motion. And because the motion is constant, because you are not accelerating or decelerating or changing direction in any way you can perceive, your body interprets it as stillness. Your inner ear, the delicate fluid-filled organ that detects changes in velocity, feels nothing. Gravity holds you to the surface with the same steady pull it always has. The air around you moves with you. The ground beneath you moves with you. And your brain, which evolved to detect threats on the African savanna, not to intuit orbital mechanics, shrugs and tells you that you're standing still. But let's complicate it, because the rotation of the Earth, as fast as it is only the first layer. The planet isn't just spinning in place like a top on a table, it's also moving through space. Specifically, it's orbiting the Sun. And that motion is so much faster than the rotation that the rotation starts to look quaint by comparison. Earth travels around the Sun at approximately 67,000 miles per hour. 67,000. For context, a commercial airliner cruises at about 500 miles per hour. The fastest jet ever built, the Lockheed SR-71 Blackbird, topped out at just over 2,200 miles per hour. The speed of sound is 767 miles per hour at sea level. The Earth, this massive rock you're standing on, is moving through space at a velocity 87 times faster than a 747, 30 times faster than the Blackbird, and nearly 90 times the speed of sound. Put another way, Earth is moving at Mach 90. That's not a spacecraft. That's not a missile. That's the ground. That's the dirt under your house, the pavement outside your window, the entire surface of the planet screaming through the void fast enough that if you could somehow freeze the Sun in place and watch the Earth go by, it would cross its own diameter in roughly 6.5 minutes. The Earth is 12,756 kilometers across. In one day, the planet travels roughly 2.6 million kilometers along its orbit. That means every 24 hours, Earth moves a distance equivalent to 202 times its own diameter. Imagine standing next to a car and watching it travel 202 car lengths in a single day. Now scale that up to a planet. That's the kind of speed we're talking about. Not drifting, not coasting, hauling. And again, you feel none of it. The orbital velocity is constant. The path is smooth. The gravitational pull of the Sun keeps Earth locked in its elliptical track, and because the motion doesn't change moment to moment, your body has no way to detect it. You are a passenger on a ship so large and moving so smoothly that the ride feels like sitting still, but the ship is moving. It has been moving since the solar system formed 4.6 billion years ago. It will keep moving until the Sun dies. And every breath you've ever taken, every step, every meal, every thought happened while you were traveling at 67,000 miles per hour. The ancient Greeks didn't know this. They thought the Earth was stationary and the heavens rotated around it, which, to be fair, is exactly what it looks like if you don't have telescopes or calculus. The stars wheel overhead, the sun rises and sets, the planets wander against the fixed background of constellations, looping and reversing in ways that seem to make sense only if you assume everything is circling us. It wasn't stupidity, it was reasonable inference based on limited information and a perspective locked to the surface of the planet. Aristarchus of Samos proposed a heliocentric model in the 3rd century BC, suggesting that the Earth orbited the Sun, not the other way around. Almost no one believed him. The idea was too strange, too contrary to everyday experience. If the Earth were moving, wouldn't we feel it? Wouldn't there be a constant wind as the planet tore through space? Wouldn't birds flying west get left behind as the ground rushed eastward beneath them? These were legitimate objections in an era before Newton, before anyone understood that air and birds and people all move together with the surface because they're part of the same system. It took 1700 years for the idea to come back. Copernicus published his heliocentric model in 1543, the year he died, and even then it was controversial. Galileo saw the moons of Jupiter through his telescope and realized they were orbiting the planet, not the Earth, which suggested that maybe, just maybe, not everything in the universe revolved around us. The Catholic Church famously disagreed and placed him under house arrest for the last decade of his life. But the observations didn't stop, the math didn't stop, and eventually the weight of evidence became too much to ignore. By the time Newton published the Principia Mathematica in 1687, the heliocentric model had won, not because people liked it, not because it felt true, but because it predicted the motion of planets with a precision the old Earth-centered model could never match. And once you accept that the Earth orbits the Sun, you have to accept everything that comes with it. The speed, the scale, the fact that the stable ground beneath your feet is neither stable nor still, just moving so smoothly that stillness is the only thing your senses can detect. Here's the thing that makes it worse. Earth's rotation isn't even consistent. It changes, not by much, but enough to measure. The length of a day, the time it takes for the planet to complete one full rotation relative to the Sun, varies by a few milliseconds from day to day. Sometimes the Earth spins a tiny bit faster, sometimes it slows down. The changes are driven by a chaotic mix of factors: the movement of the atmosphere, the sloshing of the oceans, the shifting of tectonic plates, the slow churn of the molten outer core deep below the crust, even the gravitational tug of the moon as it pulls tides across the surface. Earthquakes can change the length of a day. The massive 9.1 magnitude Tohoku earthquake that struck Japan in 2011 redistributed enough mass within the Earth that it sped up the planet's rotation by roughly 1.8 microseconds. Not enough to notice, not enough to matter to anyone's wristwatch, but enough that scientists with atomic clocks could measure the difference. The planet wobbled, adjusted, and kept spinning, slightly faster than it had been the day before. The moon is slowly stealing Earth's rotational energy, tidal forces, the same forces that lift the oceans twice a day, create friction between the water and the seabed. That friction acts like a brake, gradually slowing the Earth's spin. the energy doesn't vanish. It gets transferred to the moon, which uses it to climb very slowly into a higher orbit. Every year, the moon drifts about 3.8 centimeters farther from Earth. Every year, Earth's day gets a tiny bit longer. Billions of years ago, when the moon was younger and closer, Earth's day was only about 6 hours long. The planet spun like a top. The moon loomed enormous in the sky, pulling tides so high they would have drowned continents. Time has slowed us down. The moon has dragged us toward a longer day, and it's still dragging. In another few billion years, if the sun doesn't expand and swallow both of us first, Earth's day will lengthen to the point where one side of the planet permanently faces the moon, locked in tidal synchronization the way the moon is already locked to us. But even with all that complexity, even with the wobbles and the shifts and the gradual slowing, the baseline stays absurd. Right now, you are rotating at roughly 1,000 miles per hour. You are orbiting the sun at 67,000 miles per hour. And those are just the first two layers. Those are the motions you can almost visualize, the ones tied to objects you can see, the ground and the sun, things that feel concrete even if their speeds don't. The human brain is not built for this. We evolved to track predators moving at walking speed, to judge the trajectory of a thrown rock, to estimate whether we could outrun a lion. Our entire sensory system is calibrated for motion on the scale of meters per second, maybe tens of meters per second if we're watching something fall or fly. We have no intuitive framework for thousands of miles per hour. The numbers are too big, the speeds are too smooth, and so the brain does what it always does when faced with information it can't process. It ignores it. It filters the data, smooths it into something manageable, and hands you a simplified version of reality that says you're sitting still. You're not. You never have been. From the moment you were born, you have been a passenger on a planet that spins faster than sound and orbits faster than anything humanity has ever built. And that's just the beginning, because the Earth's motion doesn't stop at the sun. The sun itself is moving. Our entire solar system is traveling through the Milky Way galaxy at a speed that makes Earth's orbital velocity look like a lazy afternoon stroll. And the galaxy isn't sitting still either. It's falling towards something, pulled by gravity across distances so vast that light takes millions of years to cross them. Every layer you peel back reveals another motion, another speed, another frame of reference, sliding past the one beneath it. The universe is not a fixed stage. It's a cascade of nested movements, each one faster and larger than the last, and we're caught in the middle of it, spinning and orbiting and falling through space in directions we can't see toward destinations we've only recently begun to understand. And all of it, every bit of this frenetic cosmic motion, is happening while you sit there feeling nothing. The chair holds you steady, the walls stay put. The coffee mug doesn't slide, and somewhere deep in your brain, the part that still thinks like a primate on the savannah, the part that needs the world to make sense at human scale, whispers the same comfortable lie it's been whispering since before you were born. You are still, the world is calm, nothing is moving, but the solar system doesn't care what your brain whispers. It's already halfway across the galaxy from where it was when your grandparents were born. And it's not slowing down. Solar system's grand tour, racing through the Milky Way, the sun is not sitting still either. If you thought the Earth's motion was disorienting, if 67,000 miles per hour around the sun felt like enough velocity for one planet to carry, brace yourself. Because the sun, that massive nuclear furnace holding our entire solar system together, is itself screaming through the Milky Way galaxy at a speed that makes Earth's orbit look like a crawl, and it's dragging all of us with it. The solar system orbits the center of the Milky Way at approximately 515,000 miles per hour. Some measurements put it closer to 492,000 miles per hour. The exact number depends on which study you read and how the measurements were taken, but the order of magnitude is consistent, 500,000 miles per hour, give or take. That is the speed at which the Sun, along with all 8 planets, every asteroid, every comet, every speck of dust in the Kuiper Belt, and every probe we've ever launched, is traveling through space right now. For context, that's roughly 7.5 times faster than Earth orbits the Sun. It's 200 times faster than a speeding bullet. It's 700 times the speed of sound. If you could somehow stand outside the galaxy and watch our solar system go by, we would cross a distance equal to the width of the United States in less than 6 seconds. We would lap the circumference of the Earth in under 50 seconds. In 1 hour, the Sun travels a distance equivalent to more than 12 times the span from the Earth to itself. We are not drifting through the galaxy, we are tearing through it. And yet, again, you feel nothing. The motion is so smooth, the scale so large, that there is no reference point your body can latch onto. The stars in the night sky appear fixed because they are so far away that even at 500,000 miles per hour, it takes thousands of years for their positions to shift noticeably relative to us. The Sun rises and sets the same way it always has. The planets follow their predictable orbits. From inside the system, everything looks orderly, stable, unchanging. From outside, we are a blur. To understand where we're going, you need to understand where we are. The Milky Way is a barred spiral galaxy, a flat disk of stars, gas and dust, roughly 100,000 light-years across, with a dense central bulge and several spiral arms curving outward like water swirling down a drain. Our solar system sits in a relatively quiet region called the Orion Arm, sometimes referred to as the Orion Spur, a minor structure branching off one of the galaxy's major spiral arms. We are about 26,000 light-years from the galactic center, roughly halfway out from the core to the edge. In galactic terms, we live in the suburbs, not in the crowded, chaotic downtown where stars are packed close together and supernovae go off like fireworks. Not in the empty outer reaches where matter thins out and the night sky goes dark. We live in a middle-class neighborhood where stars are spaced comfortably apart and the likelihood of a nearby stellar catastrophe is mercifully low. That location matters. If we lived closer to the galactic center, the night sky would be ablaze with millions of stars packed so tightly that darkness would be a foreign concept. Planets orbiting stars near the core would experience radiation from nearby supernovae, gamma-ray bursts, and the intense X-ray emissions from the supermassive black hole lurking at the galaxy's heart. Life, if it could arise at all, would face constant existential threats from the violent stellar environment. Out here in the Orion Arm, things are calmer. The stars are older, more stable. The heavy elements necessary for rocky planets and organic chemistry have had time to accumulate from previous generations of supernovae. The radiation environment is mild. We sit in what astronomers call the Galactic Habitable Zone, a region where conditions are stable enough for planets to form, cool, and potentially develop life without being sterilized by cosmic violence every few million years. But even in the suburbs, we're moving fast. The Sun's orbit around the galactic center is not a perfect circle. It's slightly elliptical, and it bobs up and down relative to the galactic plane as it goes. Every few tens of millions of years, the solar system passes through the disk of the Milky Way, a region where the density of gas and dust is higher. Some scientists have speculated that these passages could trigger increased comet activity in the outer solar system as gravitational perturbations from nearby matter nudge objects in the Oort cloud, sending them tumbling inward toward the Sun. A few researchers have even suggested a connection between these crossings and mass extinction events on Earth, though the evidence for that remains controversial and far from settled. What is not controversial is that the solar system oscillates. We move in a wave pattern, rising above the galactic plane, coasting through relatively empty space, dipping back down through the disk, and then rising again. The full cycle takes about 60 to 70 million years. We are currently a few dozen light years above the plane and rising. The speed at which we orbit depends on where we are in the galaxy. Stars closer to the galactic center orbit faster because the gravitational pull from all the mass concentrated in the core is stronger. Stars farther out orbit more slowly. If gravity were the only force at work, and if all the mass in the galaxy were concentrated at the center the way it is in the solar system with the Sun, you would expect the orbital speeds to drop off sharply as you move outward. The farther you go, the weaker the pull, the slower the orbit. That's how planets behave. Mercury orbits the Sun much faster than Neptune because it's closer to the source of gravity. The same principle should apply to stars in a galaxy, except it doesn't. When astronomers in the 1970s started measuring the rotation speeds of stars in spiral galaxies, they found something strange. Stars far from the galactic center were moving just as fast as stars closer in. In some cases, they were moving faster than the visible mass of the galaxy could account for. The rotation curves, as they're called, stayed flat instead of dropping off the way Newton's laws said they should. That should not happen unless there is more mass in the galaxy than we can see. A lot more. This was one of the first major pieces of evidence for dark matter, the invisible substance that makes up roughly 85% of the matter in the universe. We can't see it. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we've been able to detect, but it has mass. And that mass produces gravity, and that gravity holds galaxies together. Without dark matter, the outer stars in the Milky Way would be moving so fast that they would fly off into intergalactic space. The visible matter, the stars and gas and dust we can actually observe, doesn't have enough gravitational pull to keep everything bound. Dark matter provides the missing mass, forming a vast invisible halo around the galaxy that extends far beyond the visible disk and keeps the whole structure from tearing itself apart. This means the Milky Way is not what it looks like. The glowing spiral arms, the bright central bulge, the scattered clusters of stars, all of that is just the tip of the iceberg. Most of the galaxy's mass is invisible, spread out in a diffuse spherical halo that we can only detect indirectly by watching how visible matter moves through it. We live inside a structure we cannot see, held together by a force we do not understand, moving at a speed determined by the combined gravity of matter, both visible and invisible, and until very recently, we thought we had a pretty good handle on how fast that motion actually was. Then in November 2025, a team of researchers at Bielefeld University in Germany published a study suggesting that the solar system might be moving 3 times faster through the galaxy than previously thought. Not 515,000 miles per hour, 1.5 million miles per hour. The findings have not yet been confirmed by independent teams, and many astronomers are treating the claim with caution. But if it holds up, it represents a serious problem for the standard model of cosmology. Because if the Sun is moving that much faster than we calculated, then the gravitational forces holding it in orbit must be much stronger than we thought. And that means there is either more dark matter in the galaxy than current models predict, or dark matter behaves differently than we assumed, or something else entirely is going on that nobody has accounted for. The way astronomers measure the Sun's motion through the galaxy is indirect and clever. They observe radio galaxies, distant objects far outside the Milky Way that emit strong radio waves. By mapping the distribution of these galaxies across the sky, they can detect a subtle asymmetry. There are more radio galaxies visible in the direction the solar system is moving than in the direction we're moving away from. The effect is analogous to driving through rain. If you're sitting still, raindrops hit your car evenly from all directions. If you're moving forward, more drops hit the windshield than the rear window. The faster you go, the more pronounced the effect. By measuring this cosmic headwind, astronomers can calculate how fast we're traveling through space. Radio waves are useful because they can penetrate the dust and gas that block visible light. The Milky Way is full of obscuring material that makes it difficult to see objects on the far side of the galaxy or beyond. Radio astronomy cuts through that interference, allowing scientists to observe distant galaxies that would otherwise be invisible. The technique has been used for decades, and the numbers it produces have been consistent, until recently. The Bielefeld study used a more refined analysis of radio galaxy distribution and found a stronger asymmetry than expected, which implies a higher velocity. If the result is real, it suggests that either our previous measurements were systematically underestimating the speed, or something about the galaxy's rotation has changed in ways we didn't anticipate. One possibility is that the dark matter halo is more massive or more concentrated than current models predict. If there's more invisible mass pulling on the solar system, we would move faster. Another possibility is that the Milky Way's rotation is not as uniform as we thought. Galaxies are messy. They collide, merge, get pulled and twisted by the gravity of neighboring galaxies. The Milky Way is in the process of cannibalizing several smaller galaxies right now, tearing them apart and absorbing their stars. That process could create local variations in the gravitational field that affect how fast different parts of the galaxy rotate. The solar system might be passing through a region where the pull is temporarily stronger, boosting our speed beyond the long-term average. A third possibility, the one that makes cosmologists nervous, is that the standard model itself is incomplete. If the galaxy is rotating faster than the visible and dark matter can explain, then maybe there's another force at work. Maybe gravity behaves differently on galactic scales than it does in the solar system. Maybe the equations that work perfectly well for planets and stars break down when you scale them up to structures 100,000 light-years across. This is not a popular idea. The standard model has been tested exhaustively and works remarkably well. But science is not a democracy. Popularity doesn't determine what's true. Data does. And if the data says the galaxy is spinning faster than it should, then something in the model has to give. The concept of a galactic year is one of the most humbling ways to grasp the scale of our motion. A galactic year is the time it takes for the solar system to complete one full orbit around the center of the Milky Way. At 515,000 miles per hour, that trip takes approximately 230 million years. 230 million years for one lap. The last time the Sun was in the position it occupies today, the Earth was in the middle of the Triassic period. Dinosaurs were just beginning to appear. The first true mammals were tiny shrew-like creatures hiding in the underbrush. Pangaea, the supercontinent, was still intact. The Atlantic Ocean did not exist. There were no flowering plants. There were no birds. The continents looked nothing like they do today. And the Sun was right here, passing through this same patch of the galaxy on its slow, endless circuit around the core. Since the Earth formed 4.6 billion years ago, the solar system has completed roughly 20 galactic orbits, 20 laps around the Milky Way. Every mountain range that has ever risen and eroded, every ocean that has opened and closed, every species that has evolved and gone extinct, All of it happened while the sun was making its 20th trip around the galaxy. Human civilization, the entire span of recorded history, the rise and fall of empires, the invention of writing and agriculture and cities and technology, all of that fits into a sliver of the current galactic year so thin it barely registers. We have been around for less than 1/10,000th of a single orbit. In galactic terms, humanity is a flash, a blink, a brief flicker of activity on a planet that has been riding this carousel for billions of years, and the carousel itself is moving. The Milky Way is not floating in empty space. It is part of a structure called the local group, a collection of more than 50 galaxies bound together by gravity. The local group spans roughly 10 million light-years, and every galaxy in it is moving relative to every other galaxy. Some are approaching us, some are receding, and all of them are being pulled toward a much larger structure beyond the local group, a massive concentration of galaxies called the Virgo cluster, which sits about 65 million light-years away. The combined gravity of the Virgo cluster is pulling the entire local group, including the Milky Way, toward it at hundreds of kilometers per second. That motion is on top of the Sun's motion around the galactic center, which is on top of Earth's motion around the Sun, which is on top of Earth's rotation. Layer after layer after layer, each one adding velocity, each one dragging us through space faster than the one below it. From our perspective on Earth, none of this motion creates any detectable effect. The stars do not blur. The galaxies do not smear across the sky. The cosmic microwave background, the faint afterglow of the Big Bang that fills the universe, looks the same in every direction except for a tiny dipole anisotropy, a slight difference in temperature between one side of the sky and the other. That difference is caused by our motion through space. As we move toward one direction, the light from that part of the sky gets blue-shifted, appearing slightly hotter. As we move away from the opposite direction, the light gets red-shifted, appearing slightly cooler. The effect is small, but measurable, and it gives astronomers a way to calculate our absolute velocity through the universe, not relative to the Sun or the galaxy or the local group, but relative to the cosmic microwave background itself, the closest thing we have to a universal reference frame. That measurement puts our total velocity at roughly 1.3 million miles per hour. That number includes everything: Earth's rotation, its orbit around the Sun, the Sun's orbit around the galactic center, the Milky Way's motion toward the Virgo cluster, and the local group's motion relative to the cosmic microwave background. Add it all up, and that's how fast we're moving through the universe. 1.3 million miles per hour, not relative to anything nearby, relative to the structure of space-time itself. The Milky Way is enormous, a beam of light traveling at 670 million miles per hour, the fastest speed possible in this universe, would take 100,000 years to cross from one side of the galaxy to the other. If you left Earth today at the speed of light and headed straight for the galactic center, you would not arrive for 26,000 years. Your great-great-great-grandchildren, hundreds of generations removed, would still be in transit. And you would be moving as fast as the laws of physics allow. There is no shortcut. There is no faster route. Light itself, the thing that defines the cosmic speed limit, takes millennia to traverse the space we are embedded in. And we are moving through that space at 500,000 miles per hour, which sounds fast until you compare it to the scale of the galaxy and realize how astonishingly slow it actually is. The galaxy is so large that even at our absurd velocity, it will take the solar system 230 million years to complete a single loop. Traveling at more than 700 times the speed of sound, fast enough to circle the Earth in less than a minute, and the trip still takes longer than the entire history of the dinosaurs. That is the scale we are dealing with. That is the size of the structure we live inside. And the Milky Way is not even a particularly large galaxy. It is medium-sized, maybe a bit above average. There are galaxies out there 10 times larger, 100 times more massive, with trillions of stars instead of hundreds of billions, and all of them are moving, rotating, falling through space under the influence of gravity from structures even larger still. Your address is not just Earth. It is not just the solar system. Your full cosmic address includes the Orion Arm, the Milky Way galaxy, the Local Group, the Virgo supercluster, and the Laniakea supercluster, a structure so vast that it contains 100,000 galaxies and spans 520 million light-years. You live in a specific suburb of a specific galaxy, in a specific cluster, in a specific supercluster, in a specific corner of the observable universe. And every single layer of that address is in motion, spinning, orbiting, falling. Nothing is still, nothing has ever been still, and the deeper you look, the faster the motion gets. The Sun will not stay in the Orion Arm forever. Over tens of millions of years, its orbit will carry it into different regions of the galaxy. It will pass through spiral arms, where star formation is active and the radiation environment is harsher. It will drift through quieter zones where stars are older and more spread out. The journey is long, but it is not static. The galaxy is not a fixed grid. It is a dynamic, evolving system where stars migrate, gas clouds collapse, and the structure itself shifts over time. 50 million years from now, the night sky will look different. Not because the stars will have moved noticeably in their positions, but because the Sun will have carried us to a different vantage point within the galaxy, a different neighborhood with a different view. And the Milky Way itself is not done. It is on a collision course. In roughly 4.5 billion years, it will collide with the Andromeda Galaxy, the largest member of the Local Group, currently sitting about 2.5 million light-years away and approaching at roughly 250,000 miles per hour. When the two galaxies meet, they will not crash like solid objects. Galaxies are mostly empty space. The stars will pass through each other like ghosts. But the gravitational forces will be catastrophic. Stars will be flung out of their orbits. Gas clouds will collide and ignite in a frenzy of new star formation. The supermassive black holes at the centers of both galaxies will spiral inward and eventually merge, releasing a burst of gravitational waves that will ripple across the universe. The Milky Way as we know it will cease to exist. In its place will be a new, larger elliptical galaxy that astronomers have already nicknamed Milky Way. And somewhere in the chaos, if the Sun and Earth still exist, they will find themselves in a completely different galactic environment, surrounded by stars that were once part of a foreign galaxy, moving on a new trajectory through a structure that no longer resembles home. That collision is coming, not tomorrow. Not in your lifetime, or your children's lifetimes, or the lifetimes of any species likely to descend from humanity. But it is coming. The motion is already underway. Andromeda is approaching. The distance is shrinking. And there is no force in the universe capable of stopping two galaxies once they start to fall toward each other. Gravity does not negotiate. It does not pause. It pulls constantly, patiently, and it will pull until the two galaxies collide and merge and settle into a new equilibrium. We are riding a star through a galaxy that is itself falling toward its neighbors, and the neighbors are falling toward larger structures beyond them. The universe is not a collection of isolated objects sitting still in the void. It is a web of motion, a cascade of orbits and falls and gravitational dances playing out across distances so vast that human language struggles to describe them. And we are part of that web, whether we understand it or not. The chair you are sitting in is moving. The building around you is moving. The ground beneath the building is moving. The planet is moving. The sun is moving. The galaxy is moving. And every layer of that motion is smooth enough, constant enough, that your body feels none of it. But the galaxy is not moving alone. It is part of a group, and that group is moving towards something massive, something strange. And to understand what that is, we need to zoom out one more time. The local groups dance, collisions and conquerors. We need to go wider, because the Milky Way, as enormous as it is, as fast as it's moving, is not traveling alone. It is part of a family, a gravitationally bound collection of galaxies called the local group. And like any family, it's complicated, dysfunctional, and headed toward a collision that everyone can see coming but no one can stop. The local group contains roughly 38 known galaxies, though the exact count shifts as astronomers find new dwarf galaxies hiding in the noise and reclassify objects that turn out to be star clusters instead of galaxies. These galaxies are spread across a region about 10 million light-years in diameter, a distance so vast that light itself takes 10 million years to cross from one side to the other. And yet in cosmic terms, this is a neighborhood, a small cluster, a suburban cul-de-sac compared to the massive galaxy superclusters that dominate the large-scale structure of the universe. 3 galaxies dominate the local group, the Milky Way, which we've already discussed. Andromeda, also known as Messier 31 or M31, the largest galaxy in the group, sitting roughly 2.5 million light-years away. And Triangulum, also called Messier 33 or M33, the third largest member, a bit smaller and fainter than the other two, orbiting somewhere in Andromeda's gravitational sphere of influence. These 3 are the heavyweights. Everything else in the local group is a dwarf galaxy, small collections of stars with masses ranging from a few million to a few billion solar masses. For comparison, the Milky Way contains somewhere between 200 billion and 400 billion stars. Andromeda has closer to 1 trillion. Triangulum has maybe 40 billion. The dwarf galaxies barely register. Some of them contain fewer stars than a single globular cluster orbiting the Milky Way. But small does not mean irrelevant. The dwarf galaxies tell a story about how the local group formed and evolved. Many of them are satellites, smaller galaxies that orbit the Milky Way or Andromeda the way moons orbit a planet. The Milky Way has several well-known companions. The large Magellanic Cloud and the small Magellanic Cloud are the 2 most prominent, visible to the naked eye from the southern hemisphere as fuzzy patches of light. They orbit the Milky Way at distances of roughly 160,000 and 200,000 light-years, close enough that the Milky Way's gravity is slowly tearing them apart. Long streams of gas and stars trail behind them as they move, stripped away by tidal forces and pulled into the galactic disk. In a few billion years they will be absorbed completely, their stars scattered across the Milky Way's halo, their gas mixed into the spiral arms to fuel new generations of star formation. Other dwarf galaxies are even closer and even more disrupted. The Sagittarius dwarf elliptical galaxy is currently in the process of being ripped apart and consumed by the Milky Way. It sits on the far side of the galactic center from our perspective, about 70,000 light-years from Earth, and it's so dim and so thoroughly shredded that it wasn't even discovered until 1994. Astronomers found it by mapping the distribution of old stars in the Milky Way's halo and noticing a clump that didn't belong. A clump that was moving in a different direction than the rest of the halo. A clump that turned out to be the remains of an entire galaxy. The Milky Way has been eating the Sagittarius dwarf for hundreds of millions of years, and the process is still ongoing. Every time the dwarf completes an orbit around the galaxy, it loses more mass, leaving behind trails of stars that astronomers can trace like breadcrumbs leading back to the original structure. Andromeda has even more satellites than the Milky Way. At least 14 dwarf galaxies orbit Andromeda, and there are probably more that haven't been found yet. Some of them are tiny, barely distinguishable from globular clusters. Others are more substantial, with their own internal structure and ongoing star formation. The relationship between large galaxies and their satellites is hierarchical and predatory. The big galaxies grow by eating the small ones. Over billions of years, dwarf galaxies fall inward, merge with the larger structure, and add their mass to the growing giant at the center. This is how galaxies like the Milky Way and Andromeda got so large in the first place. They didn't form all at once. They assembled piece by piece, swallowing smaller galaxies and incorporating their stars into a larger whole. The local group exists because its combined mass is strong enough to keep its galaxies from being pulled apart by the expansion of the universe. This is not obvious, and it requires some explanation. The universe is expanding, space itself is stretching, and on large scales, galaxies are moving away from each other as the space between them grows. Edwin Hubble discovered this in the 1920s by measuring the redshifts of distant galaxies and realizing that the farther away a galaxy is, the faster it appears to be receding. The relationship is linear: double the distance, double the recession velocity. That relationship is described by a number called the Hubble constant, which tells you how fast space is expanding at any given distance. The current best measurements put the Hubble constant at around 73 kilometers per second per megaparsec for distant galaxies, though that number is contentious and depends on which method you use to measure it. A megaparsec is roughly 3.26 million light-years. So for every 3.26 million light-years of distance, the expansion of space adds roughly 73 kilometers per second of recession velocity. Go twice as far, and the recession velocity doubles. Go 10 times as far, and it increases tenfold. At cosmological distances, the expansion overwhelms gravity. Galaxies drift apart, and no amount of gravitational attraction can pull them back together because the space between them is growing faster than they can move through it. But within the local group, gravity wins. The combined mass of the Milky Way, Andromeda, Triangulum, and all the dwarf galaxies is enough to hold the group together against the expansion. The galaxies within the local group are not receding from each other. They are orbiting, falling, colliding. The space between them is trying to expand, but the gravitational pull is stronger, and so the expansion loses. Draw a sphere about 10 million light-years across, centered on the local group, and everything inside that sphere is gravitationally bound. Everything outside it is being carried away by cosmic expansion. The boundary between the two regimes is called the zero-velocity surface, and it marks the edge of the region where gravity still dominates over the expansion of space. A galaxy belongs to the local group if it is gravitationally bound, meaning it does not have enough speed to escape the group's combined gravity. Some galaxies sit near the edge, and it's not entirely clear whether they're members or just passers-by. The exact membership list is still being refined, but the core members, the ones clearly bound to the group, are locked in a slow gravitational dance that will play out over the next several billion years. And the choreography is already written. The Milky Way and Andromeda are on a collision course. This is not speculation. This is not a worst-case scenario. This is an observational fact, confirmed by decades of measurements. The two galaxies are moving toward each other at roughly 110 kilometers per second, and there is no force in the universe capable of stopping them. Gravity has locked them together, and in roughly 4 to 5 billion years they will collide. The discovery of this impending collision came from measuring the motion of Andromeda across the sky. Astronomers can measure two components of a galaxy's motion: the radial velocity, which tells you how fast the galaxy is moving toward or away from you along your line of sight, and the proper motion, which tells you how fast it's moving sideways across the sky. Radial velocity is easy to measure using the Doppler shift. If a galaxy is moving toward you, its light is blue shifted. If it's moving away, its light is red shifted. Andromeda's light is blue shifted, which means it's approaching. The radial velocity is about 110 kilometers per second toward us. That part has been known since the early 20th century. The proper motion is much harder to measure because it's so small. Andromeda is 2.5 million light-years away, and even though it's moving at over 100 kilometers per second, the angular motion across the sky is tiny, less than a millionth of a degree per year. For decades, astronomers couldn't measure it precisely enough to be sure. But in 2012, a team using the Hubble Space Telescope finally nailed it down by tracking the positions of individual stars in Andromeda over the course of several years and measuring how their positions shifted relative to distant background galaxies. The proper motion was detectable, and it was pointing almost directly at us, not off to the side, not a near miss, a direct hit. When the collision happens, it will not be violent in the way you might imagine. Galaxies are not solid objects. They are mostly empty space with stars scattered so far apart that the likelihood of any two stars actually colliding is effectively zero. When the Milky Way and Andromeda merge, the stars will pass through each other like two swarms of bees flying through one another. Individual stars will not hit. They will just sail past, separated by distances so vast that they might as well be in different universes, but the galaxies will still be destroyed. The gravitational forces during a galactic collision are catastrophic, not because objects hit, but because the tidal forces tear everything apart. As the two galaxies approach, their gravitational fields will distort each other. Long streamers of stars will be pulled out of both galaxies, flung into space in spectacular tidal tails that stretch for hundreds of thousands of light-years. The spiral arms will be disrupted, the disks will warp and buckle. Stars that were once in stable orbits will be thrown onto chaotic trajectories, some flung outward into the intergalactic void, others sent plunging toward the center of the merged system. The gas clouds in both galaxies will collide. Unlike the stars, gas clouds are not separated by vast empty spaces. They are diffuse and extended, and when two gas clouds collide, they compress, heat up, and trigger a burst of star formation. The collision between the Milky Way and Andromeda will ignite one of the most intense periods of star formation in the history of either galaxy. Massive blue stars will blaze to life across the merged structure, burning hot and fast before exploding as supernovae. The night sky, if anyone is still around to see it, will be spectacular. A chaotic blaze of newborn stars mixed with the remnants of two ancient spiral galaxies tearing each other apart. At the centers of both galaxies sit supermassive black holes. The Milky Way's black hole, Sagittarius A star, weighs about 4 million times the mass of the Sun. Andromeda's black hole is larger, somewhere between 100 million and 200 million solar masses. When the galaxies merge, these two black holes will eventually spiral inward toward each other. The process will take hundreds of millions of years. They will sink toward the center of the merged galaxy, dragging stars and gas with them, slowly losing orbital energy to gravitational interactions with the surrounding matter. And then, in the final moments, they will merge. Two supermassive black holes colliding, releasing a burst of gravitational waves so powerful it will ripple across the universe, stretching and compressing space-time as the signal passes. By the time the merger is complete, the Milky Way and Andromeda will no longer exist as separate entities. In their place will be a single massive elliptical galaxy. Astronomers have already given it a name, Milky Way. The combined system will contain roughly 1 trillion stars, maybe more, depending on how much mass gets flung out during the collision. The structure will be fundamentally different from either of the original galaxies. Spiral galaxies like the Milky Way and Andromeda have organized rotating disks with spiral arms, active star formation, and young blue stars lighting up the arms. Elliptical galaxies are older, quieter. They have no disks, no spiral structure. The stars orbit in random directions, creating a smooth, featureless glow. Star formation shuts down because the gas has either been used up or blown out during the merger. What remains is a population of old red and yellow stars, slowly aging in a galaxy that has settled into a stable, quiet retirement. If Earth still exists when this happens, and that's a big if, the night sky will look nothing like it does today. The Sun will be somewhere in the outer regions of Milky Way, assuming it hasn't been flung out of the galaxy entirely during the merger. The familiar constellations will be gone, scrambled by the gravitational chaos of the collision. The sky will be filled with a diffuse glow from the combined light of 1 trillion stars, far brighter than the Milky Way we see today. And depending on where the Sun ends up, we might have a clear view of the galactic core, the dense central bulge of Milky Way blazing like a second sun in the night sky. But the Sun might not be around to see it. 4 to 5 billion years from now, the Sun will be near the end of its main sequence lifetime. It will have exhausted the hydrogen in its core and started to expand into a red giant, swelling to a size large enough to swallow the inner planets. Mercury will be consumed, Venus will be consumed, Earth's fate is uncertain. Some models suggest the Sun's expansion will stop just short of Earth's orbit. Others suggest the planet will be engulfed and vaporized. Either way, Earth as a habitable world will be long gone by the time the Milky Way and Andromeda collide. The oceans will have boiled away. The atmosphere will have been stripped into space. Whatever remains will be a charred, lifeless rock orbiting a dying star in a galaxy that no longer resembles home. The collision is not unique. Galaxies collide all the time. It's one of the primary ways they grow. The universe is full of interacting galaxies, pairs and groups caught in the act of merging, their structures twisted into bizarre shapes by tidal forces. The Hubble Space Telescope has captured hundreds of images of colliding galaxies, and they are among the most striking objects in the sky. Long streamers of stars arcing between two galaxies like bridges, massive starbursts lighting up the collision zones. Distorted spirals stretched into ribbons. These are snapshots of a process that takes hundreds of millions of years to complete, frozen in time for us to study. One of the most famous examples is the antennae galaxies, a pair of spiral galaxies about 65 million light-years away in the constellation Corvus. They began colliding a few 100 million years ago, and the interaction has pulled long tidal tails out of both galaxies, giving the system its distinctive appearance. The cores of the two galaxies are still separate, but they're falling toward each other, and in another few 100 million years they will merge completely. The collision has triggered massive star formation in the regions where the gas clouds are colliding, creating thousands of young star clusters that glow bright blue in images taken by Hubble. The Milky Way has been through this before. It did not form all at once. It assembled over billions of years by merging with smaller galaxies. The evidence is written into the structure of the galaxy itself. The halo of old stars surrounding the Milky Way's disk is full of streams and clumps, the remnants of dwarf galaxies that were torn apart and absorbed. The Sagittarius dwarf that is currently being consumed is just the most recent example. Before it, there were others, and after it, there will be more. the Large and Small Magellanic Clouds will be absorbed, and then, eventually, Andromeda. Dark matter plays a critical role in all of this. The visible matter in a galaxy, the stars and gas and dust we can actually observe, makes up only a small fraction of the total mass. The rest is dark matter, an invisible substance that interacts with normal matter only through gravity. Dark matter forms vast halos around galaxies, extending far beyond the visible disk. These halos are what hold the galaxies together and provide most of the gravitational pull during collisions. When two galaxies merge, their dark matter halos merge as well, creating a larger combined halo that dominates the dynamics of the system. We cannot see dark matter directly, but we can infer its presence by watching how galaxies move and how their gravity affects the surrounding space. The rotation curves of spiral galaxies, the way stars near the edge of the disk orbit just as fast as stars closer to the center, only make sense if there is a massive dark matter halo extending far beyond the visible stars. The motions of galaxies within the local group, the way they orbit and fall toward each other, only make sense if the group contains far more mass than we can see. Estimates suggest that dark matter makes up roughly 85% of the total matter in the universe. We live in a cosmos dominated by something we cannot detect, held together by a force we can measure but not explain. Recent studies have started to complicate that picture. In 2026, researchers studying the local group found that the expansion rate within the group, the local Hubble constant, is slower than the expansion rate measured on cosmological scales. The local value comes in around 64 kilometers per second per megaparsec, compared to 73 for the distant universe. That discrepancy suggests that either the expansion of space is not uniform, or our measurements are missing something important. Another study found that galaxy groups like the local group might not need as much dark matter as previous models predicted. The dynamics of the group can be explained with less dark matter, or with dark matter distributed differently than expected. These findings are still being debated, and they may or may not hold up under further scrutiny, but they highlight how much we still don't understand about the structure and evolution of even our own neighborhood. The local group will not stay as it is. Over the next few billion years, the Milky Way and Andromeda will merge. Triangulum will likely be absorbed as well, either into Andromeda before the collision or into Milkomeda afterward. The smaller dwarf galaxies will continue to be tidied up, swallowed one by one until the local group contains only a single giant elliptical galaxy and perhaps a few small satellites that manage to avoid being consumed, and even Milkomeda will not be alone forever. The local group is part of a much larger structure, a supercluster of galaxies that is itself falling towards something even larger. The Virgo cluster sits roughly 65 million light-years away, a massive collection of over 1,000 galaxies dominated by the giant elliptical galaxy Messier 87. The Virgo cluster is the gravitational anchor of our region of the universe, and the local group is falling toward it at a few hundred kilometers per second. Eventually, over tens of billions of years, the local group will merge with the Virgo cluster, adding its mass to an even larger gravitationally bound structure. That process will take longer than the Milky Way-Andromeda collision, but it is already underway. The pull is constant, the trajectory is set, and barring some unforeseen intervention, the future is clear. There is something unsettling about the inevitability of it all. The collision is coming. We can see it. We can measure it. We can simulate it in supercomputers and watch the two galaxies tear each other apart in exquisite detail, and there is nothing anyone can do to stop it. No force, no technology, no intervention can alter the trajectory of two galaxies once they start to fall toward each other. Gravity is patient, gravity is implacable, and gravity does not care about the civilizations that might be caught in the middle. The simulations are remarkable. Astronomers feed the known masses, velocities, and positions of the Milky Way and Andromeda into computer models and let the physics play out. The models account for the gravity of both the visible matter and the dark matter halos. They simulate the interactions between the stars, the gas, and the supermassive black holes. The results are consistent across different simulations. The galaxies approach, swing past each other in a close encounter that distorts both structures, and then fall back together for a second pass. The second collision is more violent than the first. The galaxies interpenetrate, their structures tangled together, their stars mixed into a chaotic jumble. Over the next billion years, the system settles, the stars find new orbits, and the merged galaxy takes shape. The simulations show that the Sun has a decent chance of being flung into the outer halo during the merger, but a relatively low chance of being ejected from the galaxy entirely. Most stars survive the collision and end up as part of Milky Way. A small fraction, maybe 10%, get thrown out into intergalactic space, doomed to wander the void between galaxy clusters with no way to return. If the Sun is one of the unlucky ones, Earth, if it still exists, will find itself in a profoundly dark sky. No galaxy overhead, no spiral arms, no dense star fields. Just a few faint smudges of light in the distance, the other galaxies of the local group receding as the Sun drifts farther and farther from the merger site. But most likely, the Sun will stay bound to Milky Way. It will end up somewhere in the outer regions of the elliptical galaxy, orbiting in a random direction with no particular structure to guide it. The night sky will be different, but it will still contain stars. And if any form of life still exists on Earth, or on whatever worlds humanity or its descendants have managed to colonize by then, they will look up at that sky and see the result of a collision that was set in motion billions of years before they were born. The local group is a small structure in the grand scheme of the universe. 38 galaxies spread across 10 million light-years. A single cluster in a cosmos filled with millions of clusters. But it is our structure, our neighborhood. The stage on which the story of the Milky Way has played out for the last 13 billion years, and that story is nearing a major turning point. The Milky Way will not survive the next 5 billion years in its current form. It will be transformed, merged, absorbed into something larger. And the process has already started, because the local group is not just falling inward on itself, it is also falling towards something much larger, something that sits beyond the Virgo cluster, deeper in space, pulling on thousands of galaxies across hundreds of millions of light-years. A structure so massive that it dominates the motion of everything in this corner of the universe. And for decades, no one could figure out what it was. The Great Attractor, an invisible Leviathan's pull. The local group is falling. The Milky Way and Andromeda are locked in their gravitational embrace. The smaller dwarf galaxies are being consumed, and the entire structure is drifting through space at hundreds of kilometers per second. But that motion is not random. It is not the result of some ancient momentum left over from the Big Bang. Something is pulling us, something enormous, something so massive that its gravity reaches across hundreds of millions of light-years and drags thousands of galaxies toward it like leaves caught in a current. And for decades after astronomers first detected this pull, they could not see what was causing it. They call it the Great Attractor. The name sounds like something out of a carnival or a bad science fiction novel, but it is the most honest description anyone could come up with for a phenomenon that defies easy explanation. It is not a galaxy, it is not a black hole, it is not a single object at all. It is a region of space, a gravitational focal point, a place where the density of matter is so much higher than average that everything within a few 100 million light-years feels the pull, and we are moving toward it right now at roughly 600 kilometers per second. That is more than 1.3 million miles per hour. Faster than the Sun orbits the galactic center. Faster than anything in the solar system moves on its own, and we have been moving that fast for billions of years. The story starts in the 1970s with the cosmic microwave background. The CMB, as it is usually called, is the faint afterglow of the Big Bang, radiation left over from when the universe was only about 380,000 years old and cool enough for atoms to form. It fills the entire sky with a nearly uniform glow of microwave radiation, and when astronomers first mapped it in detail, they expected to see a perfectly smooth signal. What they found instead was a dipole pattern. One side of the sky was slightly hotter than average. The other side was slightly cooler. The difference was tiny, less than 1 part in 1,000, but it was there, and it was consistent. The dipole pattern is caused by motion. When you move through the CMB, the radiation in the direction you are moving gets blue-shifted, compressed into slightly higher energy, which makes it appear hotter. The radiation behind you gets red-shifted, stretched into slightly lower energy, which makes it appear cooler. The dipole is a Doppler shift on a cosmic scale. It is the universe's way of telling you how fast you are moving relative to the CMB itself, which is the closest thing we have to an absolute reference frame. And the dipole told astronomers something they were not expecting. The Milky Way was moving much faster than the rotation of the local group and the expansion of the universe could explain. The numbers did not add up. If you accounted for the Sun's motion around the galactic center and the Milky Way's motion within the local group, you still ended up with a velocity that was too high. The galaxy was being pulled by something beyond the local group, something large, something far away. By the mid-1980s, astronomers had started mapping the motion of other galaxies in our region of space using redshift surveys. They measured how fast galaxies were moving toward or away from us, corrected for the expansion of the universe, and plotted the residual velocities. What they found was that we were not alone. Hundreds of galaxies in our neighborhood were all moving in the same direction, not randomly, not scattered, all flowing together like water draining toward a single point. That point was somewhere in the direction of the constellations Triangulum Australe, Norma, and Centaurus, deep in the southern sky. The problem was that this region lies almost directly behind the center of the Milky Way from our perspective. To look in that direction, you have to look through the galactic plane, through the dense clouds of gas and dust that fill the disk. Astronomers call this region the zone of avoidance, because it is almost impossible to see anything through it in visible light. The dust absorbs and scatters the light from distant galaxies, leaving a blank streak across the sky where no galaxies can be observed. It is like trying to see through a wall. You know something is on the other side because you can feel its effects, but you cannot see it directly. For years, the Great Attractor was a ghost, a gravitational anomaly inferred from the motion of galaxies but invisible to telescopes. Astronomers could calculate where it should be. They could estimate its mass based on how strongly it was pulling on the surrounding galaxies. But they could not see it, not with optical telescopes, not with radio telescopes. The zone of avoidance blocked everything. It was not until X-ray and infrared astronomy matured that astronomers finally started to peer through the dust and see what was hiding on the other side. What they found was the Norma cluster, also known as Abell 3627, a massive collection of galaxies sitting roughly 220 million light-years from Earth, almost exactly where the Great Attractor was predicted to be. The Norma cluster is one of the most massive galaxy clusters in our region of the universe. It contains hundreds of large galaxies and thousands of smaller ones, all bound together by gravity into a single enormous structure. The total mass of the cluster is estimated at around 1,000 trillion times the mass of the Sun. That is a number so large it stops meaning anything in human terms. 1,000 trillion suns, a mass equivalent to 1,000 Milky Way galaxies packed into a region a few million light-years across. That sounds like it should be enough to explain the Great Attractor. A cluster that massive sitting roughly where the calculations said it should be. Problem solved. Except it is not. The Norma cluster is massive, but it is not massive enough. The motion of galaxies in our region of space, the strength of the pull, the sheer number of galaxies being dragged toward that point, all of it requires something even larger. Calculations suggest that the Great Attractor has a total mass of roughly 10 quintillion solar masses, 10 million billion suns. That is 10 times the mass of the Norma cluster, which means the Norma cluster is just part of the story. It is the visible tip of a much larger structure that extends beyond what we can see, hidden behind the zone of avoidance and stretching across hundreds of millions of light years. To understand what that structure is, you have to zoom out again. The universe on the largest scales is not uniform. Matter is not spread evenly through space. It clumps. Galaxies group into clusters. Clusters group into superclusters. Superclusters form long filaments and sheets separated by vast voids where almost no galaxies exist. The result is a cosmic web, a network of structure that looks like a three-dimensional spider web stretched across the universe. The Great Attractor sits at a node in that web. It is not a single cluster. It is a convergence point, a place where multiple filaments of galaxies intersect and pile up, creating a region of space where the density of matter is far higher than average. In 2014, a team of astronomers published a paper that redefined how we think about our place in the universe. Using data from redshift surveys that mapped the three-dimensional positions and velocities of thousands of galaxies, they traced the flow of matter across our region of space and defined the boundaries of the supercluster we belong to. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is enormous. It spans roughly 520 million light-years and contains about 100,000 galaxies. The Milky Way sits near the outer edge. The Virgo cluster, which we talked about earlier, sits closer to the center, and the Great Attractor sits at the gravitational center of the entire structure. Laniakea is not a static object, it is a flow pattern. The galaxies within it are all moving toward the center, pulled by the combined gravity of all the matter in the region. The Great Attractor is the point where that flow converges, the lowest point in the gravitational well. Think of it like water flowing downhill. If you drop dye into a river, the dye will follow the current, tracing the path of the water as it flows downstream. The galaxies in Laniakea are like that dye. They are following the gravitational current, and all the currents in our region of space flow toward the Great Attractor. But here is the twist. Laniakea is not gravitationally bound. The galaxies within it are moving toward the center, but they are not moving fast enough to stay together. The expansion of the universe, driven by dark energy, is pulling everything apart faster than gravity can pull it back together. Over the next tens of billions of years, the galaxies in Laniakea will drift farther and farther from each other, and the supercluster will dissolve. The flow toward the Great Attractor will slow, stop, and eventually reverse as dark energy takes over and pushes everything apart. In the long run, gravity loses, the universe expands, the distances grow, and the structures we see today will be torn apart by the accelerating expansion of space. But that is a problem for the distant future. Right now, gravity is still winning, and the Great Attractor is still pulling. The Milky Way is moving toward it at 600 kilometers per second. To put that in perspective, that is roughly 2 million kilometers per hour. In 1 hour, the Milky Way travels a distance greater than the distance from the Earth to the Moon. In 1 day, we move roughly 50 million kilometers toward the Great Attractor. In 1 year, we move about 3,000 kilometers. We have been moving that fast for billions of years, and we will keep moving that fast for billions more. The pull is relentless. It does not fluctuate. It does not pause. Every second we are dragged a little closer to the gravitational center of Laniakea. The motion is smooth enough that we do not feel it. The galaxies around us are moving in the same direction at roughly the same speed, so from our perspective, nothing seems to change. The stars stay in their familiar constellations. The galaxies we can see with telescopes stay where they have always been. But the whole neighborhood is sliding through space together, pulled by a force we can measure but only partially see. The Great Attractor is not the only structure pulling on us. Beyond Laniakea, there are other superclusters, other concentrations of mass, other gravitational wells. Some of them are pulling us in directions that partially counteract the pull of the Great Attractor. One of the most interesting recent ideas is the concept of a dipole repeller, a vast, underdense region of space on the opposite side of the sky from the Great Attractor. An underdense region has less matter than average, which means it exerts less gravitational pull. If you are surrounded by regions of average density and one region has much less matter, the net effect is that you get pushed away from the underdense region and pulled toward the overdense regions. The dipole repeller, if it exists, would be pushing us away from one direction at the same time the Great Attractor is pulling us in the other. The result is a stronger net motion toward the Great Attractor than either force would produce on its own. This is Gauss's theorem at work. The theorem, named after the mathematician Carl Friedrich Gauss, states that the gravitational field at any point in space is determined not by the total mass of the universe, but by the distribution of mass around that point. An uneven distribution creates a net acceleration. If there is more mass in one direction than another, you accelerate toward the side with more mass. The Great Attractor is an overdensity. The dipole repeller is an underdensity. Together, they create a gravitational landscape that determines how galaxies in our region of space move. The details are still being worked out. The dipole repeller is harder to map than the Great Attractor because it is defined by an absence of galaxies rather than a concentration of them. Finding nothing is always harder than finding something, but the data so far suggest that it is real and that it plays a significant role in shaping the flow of galaxies across Laniakea. The universe is not just a collection of objects sitting in space. It is a dynamic system where the distribution of matter determines motion, and motion reveals the distribution of matter. The two are inseparable. One of the strangest things about the Great Attractor is how long it took us to find it. The pull has been there the entire time, shaping the motion of galaxies for billions of years. But we only noticed it in the 1970s, and we only started to understand it in the 1990s and 2000s. For most of human history, we had no idea we were moving. We thought the stars were fixed. We thought the Earth was the center of the universe. Even after Copernicus and Galileo and Newton, even after we understood that the Earth orbits the Sun and the Sun orbits the galaxy, we still did not grasp the full scale of our motion. It was not until we could measure the cosmic microwave background and map the three-dimensional distribution of galaxies that we finally realized we are part of a flow, a current, a vast river of galaxies streaming toward a point in space we cannot fully see. The Great Attractor sits at a distance of roughly 150 to 250 million light-years, depending on which estimate you use. That means the light we see from the galaxies in that region left them 150 to 250 million years ago. We are not seeing the Great Attractor as it is today. We are seeing it as it was in the distant past, long before humans existed, long before the dinosaurs went extinct, long before the continents took their current shapes. The light has been traveling through space for hundreds of millions of years, and it is only just now reaching our telescopes. By the time we see it, the structure has already changed. Galaxies have moved, clusters have merged, the gravitational landscape has shifted. We are always looking at the past, and the farther we look, the older the past becomes. This creates a strange situation. We can measure the pull of the Great Attractor. We can calculate how fast we are moving toward it. We can map the flow of galaxies across Laniakea and trace the currents back to their source. But we cannot see the source as it is right now. We can only see it as it was. The present state of the Great Attractor is hidden from us by the finite speed of light. It will remain hidden until the light from today's Great Attractor has had time to travel the 150 million light-years to reach us. And by the time that light arrives, we will have moved closer, the structure will have evolved further, and the present will once again be out of reach. This is one of the fundamental frustrations of cosmology. The universe is so large and light is so slow that we can never see the present state of distant objects. Everything we observe is a snapshot of the past. The farther away something is, the older the snapshot. The most distant galaxies we can see with the James Webb Space Telescope are so far away that their light has been traveling for more than 13 billion years. We are seeing them as they existed when the universe was less than 1 billion years old. Those galaxies no longer look the way they do in our images. They have evolved, merged, changed beyond recognition. But we will never see what they look like today because the light showing us their current state will not reach Earth for billions of years, and by then humanity will almost certainly be gone. The Great Attractor is closer, but the same principle applies. We see the past, we measure the present through its effects, and we predict the future using models that depend on assumptions about dark matter, dark energy, and the large-scale structure of the universe. Those models are good. They match the data. They make predictions that have been tested and confirmed, but they are not perfect. There are still gaps, still uncertainties, still places where the observations do not quite line up with the theory. One of those gaps is the mass of the Great Attractor. The Norma cluster is visible. It is real. It sits almost exactly where the calculations said the Great Attractor should be. But its mass is not enough. The pull we measure, the motion of galaxies across Laniakea, the strength of the gravitational field, all of it suggests something larger. Either there is more mass hiding behind the zone of avoidance that we have not yet detected, or the distribution of dark matter in that region is different than we thought, or our models of how gravity works on these scales are missing something. All three possibilities are uncomfortable. The first means our maps of the universe are incomplete. The second means dark matter is more complicated than the simple halo models suggest. The third means the standard model of cosmology, the framework that has guided the field for decades, might need adjustment. Astronomers are still working on it. New telescopes, new surveys, new techniques for mapping the three-dimensional distribution of galaxies are slowly filling in the gaps. The zone of avoidance is being penetrated bit by bit using wavelengths of light that can pass through dust, infrared, radio, X-ray. Each new observation adds a piece to the puzzle, but the puzzle is enormous, and the pieces are scattered across hundreds of millions of light years. It will take time. It always does. The motion toward the Great Attractor is not the only large-scale motion we are part of. There are other flows, other attractors, other currents pulling galaxies in different directions. The Shapley supercluster, an even more massive concentration of galaxies sitting roughly 650 million light-years away, exerts a pull on Laniakea. The Perseus-Pisces supercluster, another giant structure, pulls from a different direction. The universe is full of these gravitational currents, overlapping and interfering, creating a complex flow pattern that determines how galaxies move on the largest scales. The Great Attractor is just the closest and strongest of these attractors. It dominates our local motion, but it is not the whole story. Some researchers have speculated about even larger structures beyond what we can currently map. Structures so vast that they span billions of light-years and influence the motion of entire superclusters. These ideas are controversial and not yet supported by strong evidence, but they hint at the possibility that the universe is structured on scales larger than we have yet been able to observe. The cosmic web that we see, the filaments and voids and clusters, might be just one layer of a hierarchy that extends further than our telescopes can reach. And if that is true, then the Great Attractor, as massive and mysterious as it is, might be just one node in an even larger network. There is something humbling about the Great Attractor, not just its size, though the size is overwhelming. Not just its power, though the fact that it can drag the Milky Way across hundreds of millions of light-years is staggering. What is humbling is the reminder that we are not in control, we are passengers. The Milky Way is not steering, it is not choosing its path. It is falling, pulled by forces that dwarf anything humanity has ever built or imagined, and there is no way to stop it, no way to change course, no way to opt out of the journey. We are locked into this motion by gravity, and gravity does not negotiate. The destination is not certain. The Great Attractor is pulling us, but dark energy is pushing everything apart. Over the next few billion years, the two forces will compete. Gravity will continue to pull galaxies toward the center of Laniakea. Dark energy will continue to accelerate the expansion of space. Eventually, dark energy will win. The distances will grow too large, the pull will weaken, and the flow will stop. The galaxies of Laniakea will drift apart, carried by the expansion into isolated islands, separated by voids that grow wider every year. In the far future, tens of billions of years from now, the Milky Way will be alone. The other galaxies will have receded beyond the horizon of visibility, their light redshifted into invisibility by the relentless expansion of space. The night sky will be empty, no distant galaxies, no great attractor, just the stars of our own galaxy and the darkness beyond. But that is not today. Today we are still part of the flow. We are still moving toward the Great Attractor at 600 kilometers per second. And if you want to understand just how fast that is, if you want to put a number on the total velocity of your motion through the universe, you need to add it all up. Earth's rotation, Earth's orbit around the Sun's orbit around the galactic center, the Milky Way's motion toward Andromeda, the local group's motion toward the Virgo cluster, and the pull of the Great Attractor dragging everything in Laniakea toward the center. Add it all together, and the number is staggering. More than 1 million miles per hour, maybe closer to 1.3 million depending on how you do the math. But even that is not the full story, because velocity is relative. You can only measure how fast you are moving compared to something else. Compared to the chair you are sitting in, you are not moving at all. Compared to the center of the Earth, you are moving at 1,000 miles per hour. Compared to the Sun, 67,000 miles per hour. Compared to the galactic center, 500,000 miles per hour. Compared to the Great Attractor, even faster. And compared to the cosmic microwave background, the faint glow of radiation left over from the Big Bang, you are moving at a speed that represents the sum of all these motions combined. The CMB is the universe's ultimate reference frame, the one thing that is not moving relative to anything else, because it fills all of space uniformly. And when you measure your motion relative to the CMB, you get the closest thing to an absolute velocity that exists in this universe. That measurement, the dipole in the cosmic microwave background, is what started this whole investigation. It is the clue that led astronomers to discover the Great Attractor in the first place. And it is the tool that will let us measure our motion with ever greater precision as our instruments improve. The dipole is always there, always visible, a faint pattern in the microwave sky that tells us how fast we are moving and in what direction. It is the universe's speedometer, and it never lies. Cosmic microwave background, the universe's ultimate speedometer. The Great Attractor is pulling. Laniakea is flowing. Thousands of galaxies are streaming toward a gravitational focal point we can barely see, dragged by forces that dwarf anything in our immediate neighborhood. And all of that motion, all of those layers, Earth spinning, Earth orbiting, the Sun circling the galaxy, the Milky Way falling toward Andromeda, the local group drifting toward Virgo, and the pull of the Great Attractor on top of it all, every single bit of it is relative. Relative to something else. The Earth's rotation is measured relative to the Sun. The Sun's orbit is measured relative to the galactic center. The galaxy's motion is measured relative to Andromeda or the Virgo cluster or the Great Attractor. Every velocity we've discussed so far depends on choosing a reference frame, a starting point, something to measure against. But what if you want to know how fast you are really moving? Not relative to the Sun or the galaxy or some distant cluster, really moving, absolutely moving. Moving in a way that does not depend on where you choose to stand or what you decide to measure against. Is there such a thing as absolute motion in a universe where everything is moving and nothing sits still? The answer is yes, sort of. There is one reference frame that comes closer to absolute than anything else we have. It is not a galaxy, it is not a star, it is not a physical object you can point a telescope at. It is a glow, a faint, uniform sea of microwave radiation that fills every corner of the observable universe. It is the oldest light in existence, the afterglow of the Big Bang itself, and it is the closest thing cosmology has to a universal speedometer. It is called the cosmic microwave background. And when you measure your velocity against it, the number you get is the sum of every layer of motion we have talked about so far, added together into one final staggering total. Roughly 1.3 million miles per hour. That is how fast you are moving right now through the universe. Not relative to the chair you are sitting in, not relative to the Earth or the Sun or the galaxy. Relative to the structure of space-time itself. To understand what the cosmic microwave background is and why it matters, you need to go back to the beginning. Not the beginning of your life or the beginning of human history, the beginning of everything. Roughly 13.8 billion years ago, the universe began in an event we call the Big Bang. It was not an explosion in space, it was an expansion of space. The universe did not start at a point and then blow outward into a pre-existing void. Space itself began at that moment, and it has been stretching ever since, carrying matter and energy along with it. In the first fractions of a second, the universe was unimaginably hot and dense, so hot that matter as we know it could not exist. Protons and neutrons had not yet formed. Atoms were impossible. The universe was a seething plasma of fundamental particles and radiation, so tightly packed that light could not travel more than a tiny distance before colliding with something and scattering in a different direction. The whole cosmos was opaque, a glowing fog where photons bounce endlessly from particle to particle with no clear path through. As the universe expanded, it cooled, the density dropped, the temperature fell. After about 380,000 years, the universe had cooled enough that protons and electrons could combine to form hydrogen atoms. This moment is called recombination, though the name is misleading because the protons and electrons were combining for the first time, not recombining. Before recombination, the universe was opaque. Photons could not travel freely. After recombination, the fog lifted. The photons that had been trapped, scattering endlessly through the plasma, were suddenly free to travel through space without obstruction. The universe became transparent, and the light from that moment, the light that was released when the fog cleared, has been traveling through space ever since. That light is the cosmic microwave background. It is the oldest light in the universe, a snapshot of what the cosmos looked like 380,000 years after the Big Bang. When it was released, it was hot. The temperature of the universe at recombination was about 3,000 degrees Kelvin, hot enough to glow with visible light. If you had been there, floating in space at that moment, the sky in every direction would have blazed with a dull red glow, the color of molten metal. But the universe has been expanding for nearly 14 billion years since then, and the expansion has stretched the light, stretched the wavelengths, shifted the radiation from the visible spectrum into the microwave spectrum. What was once a brilliant red glow is now a faint microwave hum, cooled by the expansion to just 2.725 degrees above absolute zero. The cosmic microwave background fills the entire universe. It is everywhere. No matter where you point a radio telescope, no matter what direction you look, the CMB is there, glowing faintly at microwave frequencies. It is the most uniform thing in nature. If you measure the temperature of the CMB in one part of the sky and then measure it in the opposite direction, the temperatures will match to within a few parts in 100,000. That level of uniformity is staggering. It means the early universe, at the moment the light was released, was almost perfectly smooth. Almost, but not quite. There are tiny variations, tiny hot spots and cold spots, fluctuations of a few millionths of a degree. Those fluctuations are the seeds of all the structure in the universe today. The galaxies, the clusters, the superclusters, the cosmic web, all of it grew from those tiny ripples in the temperature of the CMB. The CMB was predicted before it was discovered. In 1948, a physicist named Ralph Alpha, working with George Gamow and Robert Herman, published a paper calculating what the early universe should have looked like if the Big Bang theory was correct. They predicted that the universe should be filled with a faint background of radiation left over from the moment of recombination. They even estimated the temperature. Their calculation was crude, but it was in the right ballpark. The radiation should have cooled to about 5 degrees Kelvin by now, they said. Close enough. Nobody took it seriously. The Big Bang theory itself was controversial in the 1940s and 50s. Most astronomers favored the steady-state theory, which held that the universe had no beginning and no end. It simply existed, eternal and unchanging, with new matter constantly being created to fill the voids left by expansion. The idea of a cosmic microwave background, a relic from a primordial fireball, seemed too strange, too speculative, too hard to test. So the prediction sat in the literature, ignored, for nearly 2 decades. Then in 1965, 2 radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing a new radio antenna designed to detect faint signals from space. They pointed the antenna at the sky and immediately picked up noise, a faint hiss that came from every direction and would not go away. They checked the equipment, They cleaned the antenna. They even evicted a pair of pigeons that had been nesting inside and scrubbed away the droppings, thinking the mess might be causing interference. The noise persisted. No matter what they did, no matter where they pointed the antenna, the hiss was there. Uniform, constant, unexplained. Penzias and Wilson had no idea what they were looking at. They were engineers, not cosmologists. But word got around, and eventually someone pointed them to Alpha's old paper. The temperature of the noise matched the predicted temperature of the cosmic microwave background almost perfectly. The hiss was not interference, it was not a flaw in the equipment. It was the echo of the Big Bang, the afterglow of the universe's birth, arriving at Earth after traveling for nearly 14 billion years. Penzias and Wilson had accidentally discovered the most important piece of evidence for the Big Bang theory ever found. They won the Nobel Prize in 1978. The discovery convinced most astronomers that the Big Bang was real. The steady-state theory collapsed. There was no way to explain the CMB without a hot, dense beginning to the universe. The radiation was there. It was real. It was exactly what the Big Bang predicted. And once astronomers started studying it in detail, they realized the CMB was far more useful than anyone had imagined. It was not just evidence for the Big Bang, it was a map, a record, a snapshot of the universe in its infancy that contained clues about how structure formed, how galaxies grew, and how the cosmos evolved from a smooth fireball into the lumpy, clumpy web of galaxies we see today. But the CMB is also something else. It is a reference frame, the closest thing we have to a universal rest frame, a fixed background against which all motion can be measured. Here is why that matters. In normal life, velocity is always relative. You measure your speed relative to the ground, or relative to the car next to you, or relative to the air rushing past. There is no such thing as absolute speed. You cannot ask how fast you are moving without specifying what you are moving relative to. Even in space, the same rule applies. The Earth's velocity is measured relative to the Sun. The Sun's velocity is measured relative to the galactic center. The galaxy's velocity is measured relative to other galaxies. Every measurement depends on choosing a reference frame. But the CMB is different. The CMB is not moving. It is not a thing in the sense that a galaxy or a star is a thing. It is a field of radiation that fills all of space uniformly. It has no velocity because it is everywhere. It is not traveling from one place to another. It just is. And because it is uniform, because it looks the same in every direction, except for the tiny fluctuations we mentioned earlier, you can use it as a reference frame. You can measure your velocity relative to the CMB by looking at how the radiation is Doppler shifted as you move through it. If you are moving toward one direction, the light from that direction gets blue shifted, compressed to slightly higher energy, which makes it appear slightly hotter. If you are moving away from the opposite direction, the light gets redshifted, stretched to slightly lower energy, which makes it appear slightly cooler. The pattern this creates is called a dipole anisotropy, and it is one of the most important measurements in cosmology. The dipole was first detected in the late 1970s, shortly after the CMB itself was discovered. Astronomers pointed radio telescopes at the sky and measured the temperature of the CMB in different directions. They found that one side of the sky was slightly hotter than the other. The difference was tiny, less than 1 part in 1,000, but it was consistent. The hotter side was in the direction of the constellation Leo. The cooler side was in the opposite direction. The pattern was exactly what you would expect if the Milky Way was moving through the CMB at high speed. The dipole is not caused by structure in the early universe. It is not a feature of the Big Bang. It is caused by motion. Our motion, the motion of the Earth, the Sun, the galaxy, the local group, all of it combined into one net velocity relative to the CMB. When you measure the dipole, you are measuring the sum of every layer of motion we have talked about in this video. Earth's rotation, Earth's orbit around the Sun, the Sun's orbit around the galaxy, the Milky Way's motion toward Andromeda, the local group's motion toward the Virgo cluster, and the pull of the Great Attractor dragging us across Laniakea. All of it adds up. All of it shows up in the dipole. The first measurements were crude. The early radio telescopes did not have the sensitivity to map the dipole with high precision. They could detect it, but the error bars were large. Over the next few decades, better instruments refined the measurement. In 1989, NASA launched the Cosmic Background Explorer satellite, known as COBE. COBE carried 3 instruments designed to study the CMB in unprecedented detail. One of them, the Differential Microwave Radiometer, or DMR, mapped the temperature of the CMB across the entire sky at multiple frequencies. The DMR confirmed the dipole and measured its amplitude with far greater precision than had been possible before. The temperature difference between the hot side and the cold side of the sky was about 3.3 millikelvin. That tiny difference, combined with the known temperature of the CMB, allowed astronomers to calculate our velocity. The number they got was 627 kilometers per second. That is roughly 1.4 million miles per hour. The direction was toward a point in the sky near the border of the constellations Hydra and Centaurus, not far from the Great Attractor. The measurement was clean. The uncertainty was small. For the first time, astronomers had a precise number for the total velocity of the local group relative to the cosmic microwave background, and the number was enormous. Later missions refined the measurement even further. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, improved the precision. The Planck satellite, launched in 2009, pushed it even further. Planck's final measurement of the CMB dipole gave a temperature difference of 3.362 millikelvin and a velocity of 631 kilometers per second, with an uncertainty of less than 1%. That is as close to a final answer as we are likely to get with current technology. The local group is moving at 631 kilometers per second relative to the cosmic microwave background. That is our absolute velocity, the speed at which we are traveling through the universe independent of any local reference frame. But the dipole is not just a number, it is a clue, a piece of evidence that points to the existence of large-scale structure beyond what we can easily see. Because the velocity the dipole reveals, the 631 kilometers per second, is faster than the motions of the local group alone can explain. If you add up the velocity of the Milky Way within the local group and the motion of the local group toward the Virgo cluster, you get a number that is too small. Something else is pulling, something farther away, something more massive. The dipole was one of the first hints that the Great Attractor existed. It was evidence, written into the temperature pattern of the oldest light in the universe, that we are being dragged by forces operating on scales far larger than the local group. To understand how the dipole works, imagine you are standing in a rainstorm. If you are standing still, the rain hits you evenly from above. Drops fall on your head, your shoulders, your arms, all at roughly the same rate. Now start running. Suddenly more drops hit your face and chest than your back. The faster you run, the more pronounced the effect. You are not changing the rain. You are just changing your motion relative to it, and that motion changes how the rain appears to be distributed. The CMB dipole is the same idea, except instead of rain, it is photons. Instead of running through a storm, you are hurtling through a sea of microwave radiation at more than 1 million miles per hour. The radiation in the direction you are moving gets compressed, blue-shifted, and appears hotter. The radiation behind you gets stretched, redshifted, and appears cooler. The universe has not changed. Your motion through it has revealed a pattern that was invisible when you thought you were standing still. The dipole is the largest anisotropy in the CMB by far. It dwarfs all the other temperature fluctuations. The tiny hot and cold spots that cosmologists study to learn about the early universe, the fluctuations that seeded galaxies and clusters, are measured in microkelvin. The dipole is measured in millikelvin, roughly 1,000 times larger. That makes it easy to detect, but it also means you have to subtract it before you can study the other fluctuations. If you want to see the primordial structure in the CMB, the patterns left over from the Big Bang, you first have to remove the dipole caused by your own motion. Otherwise, the signal you are trying to measure is completely swamped by the Doppler shift from your velocity through space. This is one of the most counterintuitive things about cosmology. The universe is expanding, galaxies are moving away from us in all directions, and yet we are also moving at very high speed in one particular direction through the cosmic microwave background. Those two facts seem contradictory, but they are not. The expansion of the universe is a stretching of space itself. It is not motion through space, it is motion of space. The galaxies are not flying away from us through a pre-existing void. The space between us and them is growing, carrying them along for the ride. The expansion is uniform. It happens everywhere at once. There is no center, no preferred location, no direction you can point to and say, that is where the expansion is coming from. But our motion through the CMB is different. It is motion through space, not motion of space. It is the result of local gravitational forces, the pull of the Virgo cluster and the Great Attractor and the other structures in our neighborhood, all tugging on the local group and accelerating us in a particular direction. That motion is real, it is measurable, and it shows up as a dipole in the CMB. The expansion of the universe does not create a dipole. Expansion affects all directions equally, so it does not change the temperature pattern of the CMB in any detectable way. Only motion through space, motion relative to the CMB rest frame, creates the dipole we observe. The existence of the dipole was predicted as soon as the CMB was discovered. If the Big Bang theory was correct, and if the local group was moving, then the CMB should be Doppler shifted. The prediction was straightforward. What was surprising was the size of the dipole. 631 kilometers per second is fast, much faster than anyone expected based on the visible matter in the local group and the nearby clusters. It implied the existence of large-scale flows of galaxies, motions driven by gravitational forces operating on scales of hundreds of millions of light-years. The dipole was evidence for the Great Attractor before anyone had found the Great Attractor. It was evidence for Laniakea before the concept of Laniakea existed. The measurement came first. The explanation came later. Breaking down the dipole into its components is complicated, but the rough picture goes like this. The Sun is orbiting the galactic center at about 230 kilometers per second. The Milky Way and Andromeda are moving toward each other at about 110 kilometers per second. The local group as a whole is moving toward the Virgo cluster at roughly 300 kilometers per second. And on top of that, the entire region, the local group and the Virgo cluster together, is being pulled toward the Great Attractor and other structures in Laniakea at another few hundred kilometers per second. These motions do not simply add up in a straight line because they point in different directions. You have to combine them as vectors, taking into account the angles and directions. When you do the math, the net result is about 630 kilometers per second in the direction of the CMB dipole. The precision of the measurement is remarkable. The Planck satellite measured the CMB temperature across the entire sky with a sensitivity of a few microkelvin. That is a few millionths of a degree. At that level of precision, you can not only detect the dipole, you can map it in exquisite detail. You can see how it varies across the sky. You can measure the exact direction of our motion. You can even detect smaller effects, like the motion of the Earth around the Sun, which creates a much tinier dipole that changes direction over the course of a year. All of this information is encoded in the temperature pattern of the CMB, waiting to be read by anyone with a sensitive enough telescope. The CMB rest frame is as close to an absolute reference frame as exists in physics. Einstein's theory of relativity tells us that there is no such thing as absolute motion, that all velocities are relative, that you can choose any reference frame you like and the laws of physics will work the same way. And that is true. The laws of physics do not care whether you are moving or standing still. They work the same either way. But that does not mean all reference frames are equally useful. Some reference frames are more natural than others. Some make the math simpler. Some reveal patterns that are hidden in other frames. The CMB rest frame is one of those special frames. It is the frame in which the universe looks most symmetric, most uniform. In the CMB rest frame, the temperature of the CMB is the same in all directions. There is no dipole. The early universe was smooth and isotropic, and the CMB reflects that smoothness. Only when you shift to a different frame, a frame that is moving relative to the CMB, does the dipole appear. This makes the CMB rest frame the natural choice for cosmology. When astronomers talk about the age of the universe, or the rate of expansion, or the distribution of galaxies, they are implicitly using the CMB rest frame as their reference. It is the frame in which the universe looks simple. It is the frame in which the Big Bang makes sense. And it is the frame in which our motion through space becomes visible as a Doppler shift in the oldest light in existence. The discovery of the CMB and the measurement of the dipole represent one of the great triumphs of modern physics. The CMB confirmed the Big Bang theory. It provided a snapshot of the early universe. It revealed the seeds of cosmic structure, and it gave us a universal speedometer, a way to measure our absolute motion through the cosmos. Every time you look at a map of the CMB, every time you see those swirling patterns of hot and cold spots, you are looking at the universe as it was 13.8 billion years ago. You are seeing the light that was released when the fog lifted, when the universe became transparent, when the first atoms formed and photons were finally free to travel through space. And if you look closely, if you measure carefully, you can see the imprint of your own motion written into that ancient light, 1.3 million miles per hour. That is how fast you are moving right now, not relative to the ground or the sun or the galaxy, relative to the cosmic microwave background, the faint glow of the Big Bang that fills the universe. You are sitting still, but the universe knows better. The dipole does not lie. The temperature difference is there, measurable, undeniable, and it tells a story about motion, about gravity, about the large-scale structure of the cosmos and the forces that shape it. But the story does not end with the dipole. Because the CMB is not the only thing revealing our motion, there are other patterns, other anomalies, other hints that something even larger might be at work. Some researchers have claimed to detect motions in the universe that cannot be explained by the structures we can see, flows of galaxies moving in directions that do not match the predictions of the standard model. They call it dark flow, and if it is real, it suggests the existence of forces or structures beyond the edge of the observable universe, pulling on everything we can see. The Great Attractor might not be the end of the story. It might just be the next chapter. The cosmic microwave background is clean. It is uniform. It is the oldest light in the universe, a snapshot of the cosmos when it was only 380,000 years old, and it looks almost exactly the same in every direction. The temperature varies by only a few parts in 100,000. That uniformity is one of the foundations of modern cosmology. It tells us the early universe was smooth, that matter was distributed evenly, that there were no massive structures lurking in the primordial fog pulling things around. The CMB is supposed to be the ultimate reference frame, the one thing in the universe that is not moving, the background against which all other motion can be measured. And for decades, that picture held up. The dipole made sense. The tiny fluctuations made sense. Everything fit. Then in 2008, a physicist named Alexander Kashlinsky at NASA's Goddard Space Flight Center published a paper that suggested something was wrong. Not wrong with the CMB itself, wrong with the assumption that the CMB reveals all the motion there is to reveal. Kashlinsky and his team had been studying the Sunyaev-Zeldovich effect, a subtle distortion in the CMB caused by hot gas in galaxy clusters. When CMB photons pass through a cluster, they scatter off the electrons in the hot gas, and the scattering shifts their energy slightly. The effect is tiny, but measurable. By mapping the Sunyaev-Zeldovich signal across the sky, astronomers can locate massive galaxy clusters, even if they are too faint or too distant to see directly in visible light. Kashlinsky's team used data from the Wilkinson Microwave Anisotropy Probe, WMAP, to map the Sunyaev-Zeldovich effect for roughly 1,000 galaxy clusters spread across a huge volume of space, clusters sitting as far as 2.5 billion light-years away. They were looking for a specific pattern. If the clusters were moving randomly, scattered in different directions with no overall trend, the Sunyaev-Zeldovich signals would be random too. But if the clusters were all moving together in the same direction, if they were part of a large-scale flow, the signals would show a dipole pattern. One side of the sky would show clusters moving toward us, the other side would show clusters moving away. The pattern would mirror the CMB dipole, except it would be caused by the motion of the clusters themselves rather than our motion through the CMB. What Kashlinsky found was a dipole, a strong one. The galaxy clusters were not moving randomly. They were flowing together in a single direction at roughly 700 kilometers per second. That is more than 1.5 million miles per hour. The flow was coherent across a region spanning billions of light-years, far larger than any structure that should exist according to the standard model of cosmology, and the direction of the flow was not aligned with the CMB dipole. It was not pointing toward the Great Attractor or the Virgo cluster or any of the known massive structures in our neighborhood. It was pointing somewhere else, toward a region of sky near the border of the constellations Centaurus and Vela, in the general direction of the Shapley supercluster, but farther, much farther. Kashlinsky called it dark flow, a term meant to evoke the mystery of dark matter and dark energy. The flow was dark in the sense that its cause was invisible. There was no structure within the observable universe massive enough to explain it. The Great Attractor, the Shapley supercluster, the entire cosmic web of filaments and voids, none of it was large enough or heavy enough to pull 1,000 galaxy clusters at 700 kilometers per second across a distance of 2.5 billion light-years. The numbers did not add up. Something beyond the observable universe, something sitting outside the horizon we can see, had to be pulling. Either that, or the standard model of cosmology was missing something fundamental. The claim was explosive. If dark flow was real, it meant the universe was not isotropic on the largest scales. Isotropy is one of the core assumptions of the lambda CDM model, the standard framework that describes the evolution of the cosmos. The model assumes that if you zoom out far enough, the universe looks the same in all directions, no preferred axis, no special direction, no large-scale flows that persist across billions of light-years. Structure exists on smaller scales. Galaxies cluster, superclusters form. But above a certain scale, roughly a few 100 million light-years, the universe is supposed to smooth out. The distribution of matter becomes uniform. The motions become random. Dark flow, if it existed, violated that assumption. It suggested there was structure, or at least gravitational influence, operating on scales much larger than the standard model allowed. The reaction from the astronomy community was immediate and divided. Some researchers were intrigued. The data looked solid. The analysis was careful. Kashlinsky was not a crank. He was a respected observational cosmologist with a track record of rigorous work. If he said the clusters were moving, then the clusters were probably moving. Others were skeptical. The Sunyaev-Zeldovich effect is subtle, and the WMAP data were noisy. Extracting a weak signal from a noisy background is always tricky, and it is easy to fool yourself into seeing patterns that are not really there. Maybe the dipole was a statistical fluke. Maybe it was caused by foreground contamination, dust or gas in our own galaxy interfering with the signal. Maybe the cluster catalog was biased, selecting certain types of clusters over others in a way that created an artificial flow pattern. In 2010, Kashlinsky and his team published a follow-up study that addressed some of the criticisms. They cross-checked the WMAP data with X-ray observations from the ROSAT satellite, which had mapped the hot gas in galaxy clusters using a completely different technique. X-rays do not suffer from the same foreground contamination as microwave observations, so if the dipole was real, it should show up in the X-ray data too. It did. The X-ray clusters showed the same flow pattern, the same direction, the same speed. 627 kilometers per second, almost identical to the WMAP measurement. The agreement between two independent datasets was compelling. It suggested the flow was not an artifact of the analysis. It was a real feature of the universe. But the skeptics were not convinced. In 2013, the Planck satellite, which had far better sensitivity and resolution than WMAP, released its own analysis of the Sunyaev-Zeldovich effect. The Planck team looked for dark flow and found nothing. No coherent motion, no dipole, no evidence that galaxy clusters were moving together on large scales. They concluded that the dark flow signal detected by Kashlinsky was likely a combination of statistical noise and systematic errors in the earlier analysis. The WMAP data, they argued, were not precise enough to detect such a weak signal reliably. The apparent flow was an illusion, a pattern that emerged from incomplete data but vanished when better data were analyzed. Kashlinsky pushed back. He argued that the Planck team had used a different method to identify clusters, a method that selected fewer and more distant clusters than his own analysis. The Planck cluster catalog was smaller and noisier, he said, which made it harder to detect the flow even if it was real. He also pointed to anomalies in the CMB itself, features that hinted at large-scale asymmetries in the universe. The CMB quadrupole, one of the largest angular scales in the temperature fluctuations, was unusually weak compared to what the standard model predicted. And there was an alignment, a strange coincidence, where several of the largest features in the CMB seemed to line up along a single axis. Some cosmologists called it the axis of evil, a tongue-in-cheek name for a pattern that should not exist if the universe were truly isotropic. Kashlinsky argued that dark flow and the axis of evil were connected, that they were both symptoms of the same underlying problem. The universe was not as uniform as the standard model assumed. There was structure on scales larger than we could see, and that structure was leaving its fingerprints on the CMB and on the motion of galaxy clusters. The debate has continued for more than a decade. New studies have come down on both sides. Some analyses claim to detect the flow, others claim to rule it out. The controversy has become one of those frustrating situations where the answer depends on which dataset you trust and which assumptions you make. The data are messy, the signals are weak, and the stakes are high because if dark flow is real, it is not just an interesting curiosity. It is a fundamental challenge to the Lambda CDM model, the framework that has guided cosmology for the last 30 years. The Lambda CDM model is built on two key ingredients. Lambda, which stands for the cosmological constant, is another name for dark energy, the mysterious force that is accelerating the expansion of the universe. CDM stands for cold dark matter, the invisible substance that makes up most of the matter in the cosmos and holds galaxies and clusters together. The model assumes the universe is homogeneous and isotropic on large scales. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in all directions. These assumptions are not arbitrary. They are based on observations. The CMB is uniform. Galaxy surveys show that the distribution of matter smooths out when you average over large enough volumes. The expansion of the universe, as measured by the redshifts of distant galaxies, is the same in all directions. Everything we can see suggests the universe is fair, that there are no special places, no preferred directions, no large-scale flows that persist across billions of light-years. Dark flow, if it exists, breaks that symmetry. A coherent motion of galaxy clusters at 700 kilometers per second across 2.5 billion light-years requires a force. Forces come from mass, and the mass required to generate that kind of pull is enormous. Koszlinski and his colleagues estimated that the source would need to be at least a few times 10 to the 14th solar masses, maybe as much as 10 to the 16th. That is the mass of thousands of superclusters, concentrated in a region sitting beyond the edge of the observable universe, beyond the horizon, beyond the reach of light, completely invisible but gravitationally dominant. This is where the idea gets strange. The observable universe has an edge, not a physical edge, not a wall or a boundary, but a horizon, a limit to how far we can see, determined by the age of the universe and the speed of light. Light has been traveling toward us since the Big Bang, but it has only had 13.8 billion years to make the trip. Anything farther than 13.8 billion light-years away, anything whose light has not had time to reach us yet, is beyond the observable horizon. We cannot see it. We cannot observe it. And according to the standard model, we should not be able to feel its gravity either because the expansion of the universe carries distant regions away from us faster than light can travel. The space between us and those regions is stretching so fast that no signal, not even a gravitational one, can cross the gap. But some researchers have argued that the horizon is not a hard cutoff. Gravity is not a signal that travels from one place to another like light. It is a curvature of space-time, a feature of the geometry of the universe itself. If there is a massive structure sitting just beyond the observable horizon, its gravity would still affect the matter inside the horizon because the two regions were connected in the past, back when the universe was smaller and denser. The structure would have imprinted its influence on the cosmic web billions of years ago, and that influence would still be visible today as a large-scale flow of galaxies. The structure itself would be invisible, carried beyond the horizon by the expansion of space, but its gravitational fingerprints would remain. This idea is controversial. Many cosmologists reject it outright. The Lambda CDM model predicts that flows should die out on scales larger than a few 100 million light-years because the expansion of space overwhelms gravity on those scales. A flow spanning billions of light-years and persisting for billions of years should not be possible unless there is something fundamentally wrong with our understanding of gravity or the expansion of the universe. Some researchers have suggested modifications to general relativity, tweaks to the equations that would allow gravity to reach farther or act differently on cosmological scales. Others have proposed that dark flow is evidence for a multiverse, a scenario where our observable universe is just one bubble in a much larger structure, and the other bubbles are pulling on us from beyond the horizon. These ideas are speculative, untestable, and not widely accepted, but they are on the table because dark flow, if it is real, does not fit neatly into any conventional explanation. The alternative is that dark flow is not real, that it is an artifact, a mirage created by biases and errors in the data. This is the more conservative position, and it is the one most astronomers lean toward. The Planck satellite, with its superior sensitivity and resolution, did not see the flow. That carries a lot of weight. Planck is one of the most successful cosmology missions ever flown. Its measurements of the CMB are the best we have. If Planck says there is no dark flow, then there is probably no dark flow. But Planck is not perfect. It had its own systematic errors, its own limitations, and the fact that Koszaliński's team saw the same signal in two independent datasets, WMAP and ROSAT, is hard to dismiss completely. The debate is not settled. One of the problems is that the Sunyaev-Zeldovich effect is not the only way to look for large-scale flows. You can also measure flows directly by looking at the redshifts of galaxies and correcting for the expansion of the universe. This technique, called peculiar velocity measurement, has been used for decades to map the motion of galaxies within a few 100 million light-years of the Milky Way. The challenge is that peculiar velocities are hard to measure at large distances because the expansion of the universe dominates the signal. The farther away a galaxy is, the faster it appears to be receding due to the expansion, and the peculiar velocity, the galaxy's motion relative to the expansion, becomes a tiny correction buried under a huge systematic effect. Measuring that correction accurately requires knowing the galaxy's distance with high precision, and distance measurements are notoriously difficult in astronomy. Despite these challenges, several large surveys have tried to map peculiar velocities across the observable universe. The Cosmic Flows Project, led by Brent Tully at the University of Hawaii, has compiled a catalogue of thousands of galaxy distances and velocities. The data show the expected flows toward the Virgo cluster and the Great Attractor. They show the motion of the local group toward the Shapley supercluster. But they do not show a coherent flow at 700 kilometers per second, extending across billions of light-years. The cosmic flows data are consistent with the lambda CDM model. They do not require dark flow. They do not require structures beyond the observable horizon. They fit the standard picture. So where does that leave us? The most honest answer is that we do not know. Dark flow is either real or it is not, and the data are not good enough yet to decide. The signal is weak, the measurements are difficult, the systematic errors are large, and the implications are profound. If dark flow is real, it tells us the universe is not as simple or as symmetric as we thought. There are influences operating on scales larger than the standard model allows. Forces pulling on us from regions we cannot see, structures beyond the horizon that dwarf everything we have mapped. If dark flow is not real, it tells us something almost as interesting. It tells us that even the best data, analyzed by careful scientists, can produce false signals, that the universe is full of noise and artifacts and patterns that look meaningful but are not, that we have to be skeptical, cautious, rigorous, and willing to question our own results even when they seem compelling. The next generation of telescopes and surveys will help settle the question. The Euclid satellite, launched in 2023, is mapping the positions and redshifts of tens of millions of galaxies across the observable universe. The Dark Energy Spectroscopic Instrument, DESI, is doing the same from the ground, targeting even more galaxies with high-precision spectroscopy. The Vera Rubin Observatory, which will begin operations soon, will survey the entire southern sky repeatedly, building a time-lapse map of the cosmos that will reveal how galaxies move and how structures evolve. These surveys will measure peculiar velocities with far better precision than anything available today. If dark flow exists, they will see it. If it does not, they will confirm its absence with much higher confidence than Planck could achieve. There are other anomalies in the data that complicate the picture. The Hubble tension, which we talked about earlier, is one of them. The expansion rate of the universe, measured locally using supernovae and Cepheid variables, does not match the rate inferred from the CMB. That discrepancy suggests either that our measurements are wrong or that the lambda CDM model is incomplete. Some researchers have speculated that dark flow and the Hubble tension might be connected, that both are symptoms of the same underlying problem, a breakdown of the standard model on large scales. Others think the two issues are unrelated, separate puzzles that will require separate solutions. Then there is the CMB itself. The dipole is clean and well understood. It is caused by our motion through the CMB rest frame, and the measurement is consistent across multiple satellites and datasets. But there are other features in the CMB that are harder to explain. The quadrupole is weaker than predicted. The octupole, the next angular scale up, is aligned with the quadrupole in a way that looks suspicious. The alignment is not strong enough to rule out as a statistical fluke, but it is strong enough to make cosmologists uncomfortable. If the universe is truly isotropic, these large-scale features should be random. They should not line up. They should not show any preferred direction. The fact that they do, even weakly, suggests there might be something going on that the standard model does not account for. One possibility is that the observable universe is not a fair sample. Maybe we live in a region that is slightly denser or slightly less dense than average. Maybe the local distribution of matter is skewed in a way that creates the appearance of large-scale asymmetry, even though the universe as a whole is isotropic. This is not a crazy idea. The observable universe is large, but it is not infinite. It spans roughly 93 billion light-years, a volume that contains hundreds of billions of galaxies. But the universe beyond the observable horizon is much larger, possibly infinite, and we have no way to sample it. If the universe is truly infinite, then every possible configuration of matter exists somewhere. We might just happen to live in a patch that looks slightly unusual. Another possibility is that the initial conditions of the Big Bang were not perfectly symmetric. The standard model assumes the early universe was smooth and isotropic, with only tiny quantum fluctuations to seed the formation of structure. But what if there were larger fluctuations, primordial inhomogeneities that got smoothed out locally but left imprints on the largest scales? Those imprints would show up in the CMB as anomalies, as patterns that do not fit the predictions of a perfectly symmetric model. Dark flow, if it is real, could be one of those imprints, a relic of the early universe, a fossil record of conditions that existed before the CMB was released. The multiverse hypothesis is another option, though it is the most speculative and the least testable. In some versions of inflationary cosmology, the Big Bang was not a single event but one of many, a bubble nucleating in a much larger inflating space. Other bubbles would have formed elsewhere, each one becoming its own universe with its own laws of physics and its own distribution of matter. If those other universes exist, and if they are massive enough, their gravity could reach across the space between bubbles and pull on the matter in our universe. Dark flow would be the result, a tug from another universe, invisible but detectable through its gravitational influence. This idea is fascinating, but it is also unfalsifiable in the traditional sense. We cannot see other universes. We cannot travel to them. We cannot test whether they exist except by looking for indirect effects like dark flow, and even then, the interpretation is ambiguous. A large-scale flow of galaxies does not prove the multiverse exists. It just proves something is pulling, and the multiverse is one possible explanation among many. Most cosmologists are uncomfortable with unfalsifiable hypotheses. If you cannot test it, it is not science, it is philosophy. And while philosophy has its place, it does not belong in a paper claiming to detect a new physical phenomenon. The tension between observation and theory in cosmology is nothing new. The field has always lived on the edge of what is measurable, pushing instruments to their limits to extract signals from noise. The discovery of the CMB, the mapping of the cosmic web, the detection of dark matter and dark energy, all of these breakthroughs came from carefully analyzing data that were barely good enough to reveal the underlying pattern. Dark flow, if it exists, would be the next step in that tradition. A signal hiding at the edge of detectability, challenging the standard model, forcing us to reconsider assumptions we thought were safe. But if it does not exist, if the signal is just noise, that is also valuable. It teaches us humility. It reminds us that the universe does not owe us clear answers, that the data are messy and the measurements are hard, and the patterns we think we see might be artifacts of our own biases and limitations. Science is not a straight path from question to answer. It is a process of trial and error, of proposing ideas and testing them and revising them when they fail. Dark flow is part of that process. A hypothesis on the table, waiting for better data to either confirm it or kill it. The lambda CDM model is not sacred. It is a tool, a framework for organizing observations and making predictions. It has been extraordinarily successful. It explains the CMB. It explains the large-scale structure of the universe. It explains the abundance of elements, the formation of galaxies, the accelerating expansion. But it is not complete. There are gaps. The nature of dark matter is unknown. The nature of dark energy is unknown. The initial conditions of the Big Bang are unknown. And there are observations like the Hubble tension and possibly dark flow that do not fit neatly into the model. Those gaps are where progress happens. They are the places where new physics might be hiding. Over the next decade, new data will flood in. Euclid, DSEA, Rubin, and other surveys will map the universe in unprecedented detail. The James Webb Space Telescope is already finding galaxies that challenge our understanding of how structure formed in the early universe. The Atacama Cosmology Telescope and other CMB experiments are mapping the microwave sky with ever greater precision, searching for subtle signals that Planck might have missed. And gravitational wave observatories are beginning to detect ripples in spacetime from merging black holes and neutron stars, opening a new window on the cosmos that might reveal features invisible to light-based telescopes. Dark flow is one piece of a larger puzzle, a hint that the universe might be more complex than the standard model allows. Whether it is real or not, it represents a question that needs answering. Are there structures beyond the observable horizon influencing the motion of galaxies we can see? Is the universe truly isotropic, or is there a preferred direction, a flow, an axis that breaks the symmetry we have assumed for so long? The answer matters because it determines whether the lambda CDM model is the final word on cosmology or just the first draft of a story that is still being written. And either way, the fact that we can ask the question, that we can measure the motion of galaxy clusters billions of light years away and argue about whether they are moving faster than they should, is a testament to how far our understanding of the universe has come. We went from thinking the Earth was the center of everything to realizing we are on a planet orbiting a star in a galaxy that is one of hundreds of billions, all of them moving, all of them part of a vast cosmic flow that stretches across distances so large that light takes billions of years to cross them. And we are not done yet. You are moving at more than 1,000,000 miles per hour right now. Not in some abstract philosophical sense, not as a thought experiment or a metaphor. You are physically, measurably, undeniably screaming through space at a velocity so extreme that if you could somehow see it from the outside, if you could step out of the reference frame you are trapped in and watch yourself go by, the speed alone would be incomprehensible. 1.3 million miles per hour. That is the number. That is the sum of every layer of motion we have talked about in this video, added together, measured against the one reference frame that comes closest to absolute in this universe, the cosmic microwave background. Let's count them again, because the human brain is not built to hold numbers like this, and repetition is the only way to make them stick. The Earth rotates at roughly 1,000 miles per hour at the equator. That is the ground beneath your feet, spinning faster than the speed of sound. The Earth orbits the Sun at 67,000 miles per hour. That is the planet itself, dragging you along on a year-long loop through space at a velocity 87 times faster than a commercial airliner. The Sun orbits the center of the Milky Way at 515,000 miles per hour. That is the entire solar system, every planet, every comet, every speck of dust in the asteroid belt, hurtling through the galaxy on a journey that will take 230 million years to complete one lap. The Milky Way is falling toward Andromeda at 110,000 miles per hour. That is two galaxies locked in a gravitational embrace that will end in a collision 4.5 billion years from now. The local group, the small cluster of galaxies we belong to, is moving toward the Virgo cluster at roughly 300,000 miles per hour. And on top of all of that, the entire region, everything within a few 100 million light-years, is being pulled toward the Great Attractor and the gravitational center of Laniakea at another 600,000 miles per hour. Every single one of these motions is happening right now, simultaneously, layered on top of each other like currents in an ocean, each one faster and larger than the one beneath it. And when you add them all up, when you combine the vectors and account for the angles and directions, the total comes to roughly 1.3 million miles per hour relative to the cosmic microwave background. That is not a guess. That is not a rough estimate. That is a measurement, precise to within a few percent, confirmed by multiple satellites over decades of observation. The dipole in the CMB does not lie. The temperature difference between one side of the sky and the other, the tiny Doppler shift caused by our motion through the ancient light of the Big Bang, is there for anyone with a sensitive enough telescope to measure, and it tells a story about motion, about gravity, about the dynamic, restless, constantly shifting nature of the universe we live in. The philosophical implications of this are staggering, though most people never stop to think about them. There is no such thing as stillness, not in the way we imagine it, not in the way our senses tell us it exists. You think you are sitting still right now because every object around you, every molecule of air, every particle of matter in your immediate vicinity is moving with you. You are all part of the same system, all caught in the same flow, and from inside that system, the system looks calm. But zoom out, pull back from the Earth, from the solar system, from the galaxy, from the supercluster. Watch the motion from a vantage point outside the flow, and what you see is chaos, not violent chaos, not the kind that destroys things, but motion on a scale so vast and so relentless that the word stillness stops having any meaning. The universe is not a stage where objects sit and occasionally move. It is a river. Everything is flowing. Everything has always been flowing, and the flow does not stop. This is not new information. Physicists have understood for more than a century that motion is relative, that there is no absolute rest frame, that you can only measure velocity by comparing one object to another. Einstein built an entire theory, special relativity, on the idea that the laws of physics look the same no matter how fast you are moving or in what direction. Velocity does not matter. Only changes in velocity, acceleration, produce measurable effects. If you are moving at a constant speed in a straight line, there is no experiment you can perform, no measurement you can take, that will tell you how fast you are going without referencing something outside your system. The universe does not care whether you think you are moving or standing still. The physics works the same either way. But that does not make the motion any less real. It just means we are terrible at perceiving it. Our senses evolved to detect changes, threats, predators moving at walking speed, objects accelerating or decelerating or shifting direction. We are not equipped to feel constant velocity. We are not built to intuit speeds measured in hundreds of thousands of miles per hour. And so the brain does what it always does when faced with information it cannot process. It ignores it, it filters the noise, smooths the data, and hands us a simplified version of reality that says we are standing still because standing still is safer, simpler, easier to navigate than the truth. The truth is that you have never been still, not for a single moment of your life. From the instant you were born, you have been spinning with the Earth, orbiting with the Sun, falling through the galaxy, dragged by forces so large and so distant that their effects are invisible at human scales. You will never be still. You will move until the day you die, and even then, the atoms that made up your body will keep moving, scattering into the soil, the air, the water, cycling through the biosphere and eventually into space as the sun expands and the earth is consumed. Motion is not something that happens to you. Motion is what you are. It is the most fundamental feature of existence in this universe. Everything that has mass and energy is moving, has always been moving, will always be moving, and the only reason we perceive stillness is because we are trapped inside a reference frame that is itself moving so smoothly that we cannot feel it. The forces driving all of this motion are gravity and inertia. Gravity pulls, inertia resists changes to motion. Together they create the patterns we observe. Planets orbit stars because gravity pulls them inward, while inertia keeps them moving forward, and the two forces balance into a stable orbit. Stars orbit the galactic center for the same reason. Galaxies fall toward each other, accelerating as the distance shrinks, because gravity never turns off and never gets weaker as long as there is mass to generate it. And on the largest scales, the scales of superclusters and cosmic voids, gravity is still pulling, still shaping the flow of matter, even as the expansion of space works against it, stretching the distances and weakening the pull. Dark matter is the invisible scaffolding that makes most of this motion possible. Galaxies do not have enough visible mass to hold themselves together at the speeds they rotate. Stars near the edge of a spiral galaxy are moving so fast that they should fly off into intergalactic space, flung outward by centrifugal force like water spinning off a wheel. The fact that they do not, the fact that galaxies are stable structures that last for billions of years, means there is more mass than we can see, a lot more. Dark matter makes up roughly 27% of the total mass energy content of the universe. It does not emit light, it does not absorb light, it does not interact with electromagnetic radiation in any way we have been able to detect. But it has mass, and that mass produces gravity, and that gravity holds galaxies together. It forms vast halos around galaxies, extending far beyond the visible disk. It clumps into filaments and nodes, creating the cosmic web that defines the large-scale structure of the universe. And it is the reason the Milky Way can orbit the galactic center at 500,000 miles per hour without tearing itself apart. We still do not know what dark matter is. We know it exists because we can see its gravitational effects. We can measure how fast galaxies rotate. We can watch how light from distant objects bends as it passes through regions filled with dark matter, a phenomenon called gravitational lensing. We can map the distribution of dark matter across the universe by observing how it clumps and clusters, but we cannot detect the particles themselves. Decades of experiments designed to catch dark matter particles colliding with normal matter have come up empty. If dark matter is made of particles, they are extraordinarily elusive, interacting with ordinary matter so rarely that even the most sensitive detectors have failed to register a single confirmed event. Some physicists have started to wonder whether dark matter is particles at all. Maybe it is something else. A modification to the laws of gravity that makes gravity stronger on large scales than Newton or Einstein predicted. A field that permeates space and affects the motion of matter without being matter itself. Or maybe it is particles, but not the kind we have been looking for. Not the kind that interact weakly with normal matter. Something more exotic, something that exists in a sector of physics we have not yet discovered. The truth is, we do not know, and that ignorance sits at the heart of the story we have been telling in this video. Dark matter is the reason galaxies move the way they do. It is the reason the cosmic web exists. It is the reason the Great Attractor can pull thousands of galaxies across hundreds of millions of light years. And we have no idea what it is made of. Dark energy is even stranger. If dark matter is the force that holds things together, dark energy is the force that is tearing everything apart. The universe is expanding, and the expansion is accelerating. Galaxies that are not gravitationally bound to each other are moving apart faster every year, and the rate of separation is increasing. This was discovered in the late 1990s when two independent teams of astronomers measured the distances and redshifts of distant supernovae and realized that the expansion of the universe was not slowing down the way everyone expected. It was speeding up. Something was pushing space apart, counteracting gravity, driving the cosmos toward a future where everything that is not bound together by gravity will drift so far apart that it becomes invisible, unreachable, lost beyond the horizon of observation. Dark energy makes up roughly 68% of the total mass energy content of the universe. That is more than dark matter. More than all the stars and galaxies and gas and dust combined. The universe is dominated by a force we do not understand, a force that does not cluster or clump or form structures. It is spread uniformly through space, a constant background pressure that does not change with time or location. The simplest explanation is that dark energy is the cosmological constant, a term Einstein added to his equations of general relativity and then later called his greatest blunder. The cosmological constant represents the energy of empty space itself, a baseline level of energy that exists even in a perfect vacuum. If that energy is positive, it acts as a repulsive force, pushing space apart. The math works. The predictions match the observations, but nobody knows why the cosmological constant has the value it does. Quantum field theory predicts a value for the energy of empty space that is 10 to the power of 120 times larger than what we observe. That is not a small discrepancy. That is one of the biggest unsolved problems in physics. The accelerating expansion changes everything. For most of the history of the universe, gravity was winning. Galaxies were pulling on each other, forming clusters, building the cosmic web. The expansion was still happening, but it was slowing down, held back by the mutual gravitational attraction of all the matter in the cosmos. Then, about 5 to 6 billion years ago, the expansion crossed a threshold. The universe had expanded enough that the density of matter dropped below a critical value, and dark energy, which does not dilute as space stretches, became the dominant force. The expansion started to accelerate, and once that acceleration began, it has not stopped. It will not stop. In the far future, tens of billions of years from now, the acceleration will have carried every galaxy beyond the local group so far away that their light will be redshifted into invisibility. The night sky will go dark. The cosmic microwave background will cool to a temperature so low that it becomes undetectable. And any civilization still around, any observers still trying to make sense of the universe, will find themselves in a cosmos that looks empty, isolated, and fundamentally different from the one we see today. But that is a problem for the distant future. Right now, the universe is still full of motion, full of structure, full of galaxies and clusters and flows that we can observe and measure and try to understand. And we are getting better at it. The tools we have today, the telescopes, the satellites, the supercomputers running simulations of cosmic evolution, are orders of magnitude more powerful than anything available even 20 years ago. The James Webb Space Telescope is finding galaxies in the early universe that should not exist, massive structures that formed faster than the Standard Model predicts. The Euclid satellite, launched in 2023, is mapping the positions and redshifts of billions of galaxies, tracing the cosmic web in 3 dimensions with unprecedented precision. The Dark Energy Spectroscopic Instrument, DESI, is measuring the expansion history of the universe by observing how galaxies cluster at different distances. These missions are not just collecting data, they are testing the foundation of cosmology, probing the limits of the lambda CDM model, searching for cracks in the framework that has guided the field for decades, and they are finding cracks. The Hubble tension, the discrepancy between the expansion rate measured locally and the rate inferred from the cosmic microwave background, is still unresolved. The impossibly early galaxies discovered by Webb are still unexplained. Dark flow, if it is real, is still incompatible with the Standard Model. These are not minor issues. They are fundamental challenges to our understanding of how the universe works. And they suggest that the next few decades in cosmology are going to be turbulent, exciting, and full of surprises. One of the biggest questions is whether the lambda CDM model is the final word or just the first draft. The model works remarkably well. It explains the cosmic microwave background. It explains the large-scale structure of the universe. It explains the abundance of light elements like hydrogen and helium forged in the first few minutes after the Big Bang, but it has gaps. Dark matter is unknown. Dark energy is unknown. The initial conditions of the Big Bang, the quantum fluctuations that seeded all the structure we see today, are inferred but not directly observed, and there are observations that do not fit cleanly. The Hubble tension, the early massive galaxies, the possible detection of dark flow, each one is a thread sticking out of the tapestry, and if you pull on it, the whole thing might unravel. Some researchers think the solution will come from new physics, a modification to general relativity that changes how gravity behaves on cosmological scales, a better understanding of quantum mechanics in curved spacetime, a theory of quantum gravity that unifies general relativity and quantum field theory into a single coherent framework. These are hard problems, the kind of problems that have stumped the smartest physicists on the planet for decades, but they are not impossible. History is full of examples where observations that did not fit the existing theory led to breakthroughs. The orbit of Mercury did not fit Newtonian gravity, and that discrepancy led Einstein to general relativity. The blackbody radiation spectrum did not fit classical physics, And that led to quantum mechanics. Maybe the Hubble tension or the early galaxies or dark flow will be the anomaly that leads to the next revolution in physics. Or maybe the lambda CDM model just needs a tweak, a small adjustment that brings the observations back into line without overturning the entire framework. The future missions that are already planned or in development will provide the data needed to answer these questions. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will have a field of view 100 times larger than the Hubble Space Telescope. It will survey the sky, mapping the distribution of galaxies and measuring the properties of dark energy with far greater precision than any previous mission. The Vera Rubin Observatory, currently under construction in Chile, will begin a 10-year survey of the southern sky, taking images every few nights and building a time-lapse map of the cosmos that will reveal how objects move, how transients like supernovae explode, and how the universe evolves over time. The Atacama Cosmology Telescope and other next-generation CMB experiments are pushing toward ever more sensitive measurements of the microwave sky, searching for subtle signals left over from the earliest moments of the universe. These instruments will not just refine existing measurements, they will open new windows. Roman will be able to detect faint galaxies that are too dim for Webb to see. Rubin will discover thousands of new asteroids, comets, and Kuiper belt objects in our own solar system, along with supernovae, variable stars, and transient events across the observable universe. The CMB experiments will search for primordial gravitational waves, ripples in spacetime generated during the inflationary epoch, the brief period of exponential expansion that occurred in the first fraction of a second after the Big Bang. If those waves are detected, they will provide direct evidence for inflation and offer a glimpse of the universe at energies far beyond anything we can reach in particle accelerators. But even with all these tools, even with all the data, there are questions that might never have answers. Why did the universe begin? What, if anything, came before the Big Bang? Is the observable universe all there is? Or is it just one bubble in a much larger multiverse? What is the ultimate fate of the cosmos? Will the expansion continue forever, carrying everything apart until the universe is cold, dark, and empty? Will dark energy strengthen, eventually tearing apart galaxies, stars, planets, atoms, in a scenario called the Big Rip? Or will something else happen, something we have not predicted because the physics at those timescales is completely unknown? The heat-death scenario is the most commonly accepted fate. If the expansion continues and dark energy remains constant, the universe will keep stretching. Stars will eventually exhaust their fuel and die. Galaxies will fade as star formation stops. Black holes will evaporate over timescales so long they defy comprehension, 10 to the power of 100 years or more. And in the end, the universe will be a cold, dark, nearly empty expanse where nothing happens, nothing changes, and nothing can happen because there is no energy left to drive any process. That is heat death, maximum entropy. The end of time, not with a bang, but with the slowest, quietest whimper imaginable. The Big Rip is less certain but more dramatic. If dark energy is not constant, if it grows stronger over time, it could eventually overwhelm every force in the universe, even the forces that hold atoms together. The expansion would accelerate so violently that galaxies would be torn apart, then stars, then planets, then molecules, then atoms. Space-time itself would be ripped to shreds in a final cataclysmic moment. The math allows for this scenario, but there is no evidence yet that dark energy is strengthening. All the measurements so far are consistent with a cosmological constant that does not change. But the measurements only cover the last few billion years. We do not know what dark energy will do over the next 100 billion years or the next trillion. We are extrapolating into a future that is so distant and so uncertain that any prediction is more speculation than science. There is another possibility that some cosmologists take seriously: the idea that the universe is cyclic, that it expands, reaches a maximum size, and then contracts, collapsing back into a big crunch. And from that crunch, a new Big Bang emerges, starting the cycle over again. In this model, the universe has no beginning and no end. It just oscillates, expanding and contracting forever. The cyclic universe solves some philosophical problems, like what came before the Big Bang. The answer is the previous cycle. But it creates new problems. What causes the bounce? How does a collapsing universe reverse into an expansion without violating the laws of physics? And how do you reconcile a cyclic model with the accelerating expansion we observe today? If dark energy is real and constant, the universe will never collapse. It will expand forever. The cyclic model requires dark energy to turn off or reverse at some point in the future, and there is no evidence that will happen. These are not questions we are going to answer in this video. They might not be questions humanity ever answers. The timescales involved are so long, the distances so vast, the energies so extreme, that we might be asking about things that are fundamentally beyond our reach. But that does not make the questions less important. They are the edges of the map, the places where known physics fades into speculation, and the fact that we can even ask them, that we have learnt enough about the universe to frame the questions coherently, is a testament to how far we have come. The story we have told in this video, the story of motion, of Earth spinning and orbiting, of the Sun racing through the galaxy, of galaxies falling toward each other and superclusters flowing across hundreds of millions of light years, all of it is a story about connection. Everything is connected. Every motion is caused by something else. Earth orbits the Sun because the Sun's gravity pulls it. The Sun orbits the galactic center because the combined gravity of stars and dark matter holds it in a stable path. Galaxies fall toward each other because gravity does not stop at the edge of a galaxy. It reaches across intergalactic space, pulling on everything within its influence. And the entire cosmic web, the filaments and voids and clusters that define the large-scale structure of the universe, is the result of gravity acting on the tiny quantum fluctuations that existed in the first moments after the Big Bang. The universe is not a collection of isolated objects. It is a system, a vast, interconnected, dynamic system where every part affects every other part. You are not separate from that system. You are part of it. The atoms in your body were forged in the cores of stars that exploded billions of years ago. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it came from stellar nucleosynthesis, the process by which stars fuse light elements into heavier ones and scatter them across space when they die. You are made of stardust. That is not a metaphor. That is a fact. And the motion of those atoms, the motion that has carried them from the cores of ancient stars to the planet you are standing on, is part of the same cosmic flow we have been describing. You are moving at 1.3 million miles per hour because the universe is moving. And the universe is moving because motion is built into its structure, woven into the fabric of space-time itself, from the moment the Big Bang began. There is something humbling about that realization. Not humbling in a depressing way, humbling in the way that reminds you how vast the universe is and how small we are within it. We are passengers on a planet that is itself a passenger on a star that is itself a passenger in a galaxy that is falling toward other galaxies in a cosmic flow that spans distances so large we can barely comprehend them. We did not choose this journey. We did not set the destination. We are just along for the ride, and the ride is extraordinary. It is a cascade of motions, each one faster and larger than the one before, building into a total velocity that would be fatal if we could somehow feel it. But we do not feel it. We sit in our chairs, we drink our coffee, we go about our lives, completely unaware that the ground beneath us is hurtling through space at speeds that make sound look slow and light look almost lazy. The universe does not care whether you understand it. It does not care whether you notice the motion or calculate the velocity or marvel at the scale. It will keep moving whether you are watching or not. Galaxies will keep falling toward each other. The expansion will keep accelerating. Dark energy will keep pushing space apart. And billions of years from now, when the sun has died and the Earth has been consumed and the Milky Way has merged with Andromeda into a single giant elliptical galaxy, the universe will still be here, still expanding, still evolving, indifferent to the tiny flash of consciousness that once existed on a rocky planet orbiting an average star in an unremarkable corner of space. But for now, we are here. We are conscious, we can observe, we can measure, we can ask questions about how the universe works and why it moves the way it does, and we can build instruments powerful enough to answer some of those questions: the James Webb Space Telescope, the Euclid satellite, the cosmic microwave background mappers, the gravitational wave detectors. All of them are eyes, extensions of human curiosity reaching into the cosmos, searching for patterns, testing theories, pushing the boundaries of what we know. And every answer we find opens up new questions, deeper questions, harder questions, questions that might take centuries to answer or might never be answered at all. That is the nature of science. It is not a destination, it is a process. A way of looking at the world that prioritizes evidence over intuition, measurement over belief, revision over dogma. And it is a process that works. It gave us the Big Bang Theory, confirmed by the discovery of the cosmic microwave background. It gave us dark matter, inferred from galaxy rotation curves and gravitational lensing. It gave us dark energy, discovered through observations of distant supernovae. It gave us the knowledge that we are moving at 1.3 million miles per hour through a universe that is 13.8 billion years old and 93 billion light-years across. Every one of those facts is a victory, a piece of the puzzle snapped into place after years or decades of painstaking work by thousands of scientists building on the work of those who came before them. And the puzzle is not finished, not even close. We have a rough outline of the universe, a sketch of how it began and how it evolved and where it might be going. But the details are still being filled in. The nature of dark matter, the nature of dark energy, the reason the Hubble constant does not match, the origin of the quantum fluctuations that seeded galaxies, the ultimate fate of the cosmos. These are not trivial questions, they are foundational, and the answers, when they come, will reshape our understanding of reality in ways we cannot yet predict. So where does that leave us? Sitting still in a universe that is anything but still, moving faster than we can perceive through a cosmos that is larger, older, and stranger than our ancestors could have imagined. Tiny, fragile, temporary, clinging to a rock that is itself clinging to a star that is itself caught in a galactic dance that will end in collision and merger and transformation. We are part of something vast, something ancient, something that does not need us but allows us to exist long enough to notice it, to measure it, to try to make sense of it. And that, in the end, is the most remarkable thing of all. Not that the universe is moving, but that we are here to see it. You are moving at 1.3 million miles per hour right now, and the most unsettling part is not the speed, it is the fact that you will never feel it. Every reference point you have ever used to measure stillness is moving with you. The chair, the floor, the air, the ground, the planet, the sun, the galaxy. All of it is caught in the same flow, falling through space together so smoothly that your body interprets the motion as nothing at all. You evolved on a spinning rock that orbits a star that circles a galaxy that is falling toward a cluster that is being pulled by forces so large they span hundreds of millions of light years, and none of it, not a single layer, feels like motion to you. That is not a flaw in your perception. That is how the universe works. Motion is only detectable relative to something else, and when everything around you is moving together, stillness becomes indistinguishable from chaos. The universe is not a stage, it is a river, and we are not standing on the shore watching it flow. We are in it. We have always been in it, and the current does not stop, it does not slow. It pulls us toward destinations we cannot see, shaped by forces we barely understand, across distance